I, Dr. Amit Sehgal, Director, Sharda Launchpad Federation, on behalf of Sharda University, Greater Noida, welcome you all to this WPMC 2024, scheduled at Greater Noida, Sharda University. The theme of this year's symposium is Secure 6G AI Nexus, where technology meets humanity, which emphasizes the increasing importance of secure and intelligent wireless communication systems, and also that 6G and AI are not just technological advancements, but also that 6G and AI have the potential to transform the way we interact with each other and with the technology. In this 4 days symposium, we will begin with today's pre-conference tutorials. And the first tutorial that we have today is on circular. I beg your pardon. So the first tutorial that we have today, we have our expert with us, Dr. Amlan Chakravarti. May I have the honor to formally introduce Dr. Amlan Chakravarti to you. He is a professor and director of the A.K. Chaudhary School of Information Technology, University of Calcutta. He is also the former Dean, Faculty of Engineering and Technology of the university during 2016-19. Dr. Amlan Chakravarti is postdoctoral fellow at the School of Engineering, Princeton University, USA during 2010-11. He has more than 20 years of experience in engineering education and research. He received the DST Boycott Fellow Award in Engineering Science 2011, Indian National Science Academy INSA Visiting Faculty Fellowship, JSPS Invitation Research Award, Erasmus Mundus Leader Award, Hamid Visiting Professorship from University of Cambridge, UK, and Shiksha Ratna Award by Department of Higher Education, Government of West Bengal, and IBM Quantum Researchers Access Award. Dr. Amlan Chakravarti has received multiple project grants in the areas of embedded system design, VLSI design, quantum computing, computer vision, cybersecurity, IoT, from various funding agencies like DST, MIT, DRDO, DAE, Ministry of Social Environment, UGC, and many others. He has also served in various social environment and technology-related projects. He has published more than 160 research papers in referred journals and conferences, 4 patents, and 1 copyright, and has graduated 16 PhD students. His areas of research are machine learning, computer vision, reconfigurable computing, cyber physical systems, VLSI, CAD, and quantum computing. Sir, we are really honored to have you here for this session. May I request our Honorable Vice Chancellor, Dr. Sibaram Khara, to formally welcome our guest for the day. Thank you, sir. May I request Dr. Amlan to please begin with today's tutorial.
Final PPT. Yeah, very good morning to all of you, to all the attendees of this conference, as well as my tutorial. And thanks to Sharda University, the Honorable Vice Chancellor Sir, the Dean, for inviting me. I am well connected with this university. I also am privileged to connect with some of the research groups and also serve this university as a distinguished visiting professor. And that means it's always great for me to come to Sharda and to connect with all of you. So what I will be speaking today, okay, is a domain which is coming up. Okay, I will not say that it's a very well-established domain. Okay, but we know that the researchers, okay, like us, should work on some of the topics, okay, which are very upcoming, okay, so that we can build and we can contribute in those technologies, because once a technology is very very much well-driven, right? You don't have much fundamental contributions to those technologies, right? And quantum computing is one of the technology which we all know is one of the really upcoming technology, right, in the global level. That means most of the advanced countries across the world have set up the quantum research in the various national labs. Top companies like Google, Microsoft, IBM, Intel, okay, what you name, okay, all have started their quantum computing stuff and quantum communication also. Ericsson, Qualcomm, okay, they are already into quantum communication. Keysight, okay, Cisco, they are all in quantum communication now. So quantum computing and quantum communication is really a very exciting topic now because it's just picking up in the industry, and there is immense challenges are there, immense problems are there, which attracts us, researchers like us, to come and to solve some of them. So obviously the time what I have today, okay, is around 1.5 hours will be not sufficient to give a full spectrum of this, okay, either quantum computing or quantum communication, because these are vast subjects. But what I will try to speak today is some of the fundamental areas, okay, so that some of you who are really want to get into this exciting domain of research, okay, can actually get the food for thoughts, okay. It's not that I will complete everything, every part of this knowledge, but I will just try to excite you with the thought process, and that's what drives research, right? You have to, when you are doing a research, you should have a thought process, right? And everyone will have a different thought process, and so the researches are so wide, okay? So let's start. So this is my topic. We are in a conference, which is a very well-known conference in communication domain, so I try to fit my title, okay? That means, okay, so how quantum communication and quantum computing, okay, will be taking the internet, the present internet we have, in the next gen. Okay, so if you tell that the current internet, which is based on classical communication and classical computing, right, when we really take it off in the quantum platform, okay, the thing will be next gen. Okay, so this will be the outline of my talk. It's a very simple. I've tried to keep. Okay, so let's start with the basics of quantum computing, and this is the scenario. What I have shown you is the progression of the computing platforms. Okay, at the extreme left was the computers which you will see in the computer museums. Right, I was lucky to be the part of Princeton and Cambridge. So if you visit those those phenomenal universities, you will find they have the computer museums, and you will keep this type of very early computers there. But what we are at the present scenario is in the middle, right? We are in the silicon computing. Silicon computing means, and you know that obviously our country, India, is also making great step in semiconductors now. Okay, so this is what we have done. Our computers have been miniaturized, and this has been miniaturized because we have from the scale of say LSI, from the scale of SSI, we will say rather. From the scale of SSI, we have reached in a zone which is now UVLSI, ultra scale VLSI. And in the ultra scale VLSI, the transistor dimensions are of the order of 1.5 nanometer. The Intel latest process is going on 1.5 nanometer, which is fantastic. Okay, right? And we have a large scale integration. So from single chip, we've gone to multi-core. From multi-core, we've gone to SoC. Right, and recently I was in Germany, in Dresden, and we are talking about chiplets. So this is a wide migration which has been done in the VLSI domain, and the entire thing is because we have reduced the size of the dimension of the transistors, and we have a very high-scale processing technology which can handle those dimensions. But when we are talking of these dimensions, we are already reaching a level where our devices are of monoatomic layer. Okay, so can we do further? So the next further thing what we can do is a paradigm shift. Is a paradigm shift from our semiconductor device-based computing okay, to computing which works on the atomic states. And that computing is what is quantum computing, and that is the extreme, left. What I show you is the atomic states. Okay, that means atomic states which can be the electron spin. Okay, it can be the nuclear polarization, right? It can be the electron charge, right? It can be also done on the photonic, the polarization of the photons. So many technologies we can look into, or it may be say a quantum trap for the ions. Okay, so there are so many things we can do once we get into this atomic properties or atomic observables of our matter, and that's a very obvious because we are squeezing into that level of dimensions. Okay, but again, having said so, okay, only reducing the dimension and getting into quantum computing is not the motivation. Okay, obviously the motivation is that can we do something better in terms of computing? Can we do something better in terms of memory? Okay, because computer means two main things. Okay, one, you have to store data, and another is to process data. Okay, so can we do something better in the storage of data? Right? Can we have something better storage of data, and can we have something better in the processing of data? If we can do all these things, then we can obviously shift the computing thought process from the current classical computing states, to the quantum. Okay. So before going into those particular things, let us just try to see that what is a quantum computer. And this is a figure which is almost 4 or 5 years ago from the IBM quantum computing system. It doesn't mean that means only IBM as a quantum computing system. There are multiple efforts has been taken, right? And you know that through the national quantum mission of our country, we are building the quantum computer. Okay, our country, some of the labs of our country will be doing the quantum hardware, and we, the quantum algorithm people, will be working on this quantum hardware. Okay, and we are very excited to see that India has taken up this. Okay, so what are the things what a quantum computer does? Okay, which are very different from a classical computer, right? So these are the three things. Okay, three things why it's called a quantum supremacy or quantum advantage. Okay, first is that quantum states. Quantum states are pretty different, and we will go into details in my lecture. Quantum states are pretty different and pretty exciting, right? When something is exciting, there are two things, okay? That means it can do something which is very different, right? Good for us, right? And in some cases, if it is exciting, that if we don't able to control it, all of our energy, that all of our efforts goes down. So we will see that there are two ways, right? Why quantum control and quantum systems are so much different, and why we have to come up with some new technology to handle. Though we know mathematically these are quantum states, which are very exciting, but we have to come up with new technology to handle those quantum states, right? And that's also a challenge, okay? Secondly is that if we are able to handle the quantum states, then what we can have is that we have exciting computing. Okay, we can have an exponential speed up in computing. Now, exponential speed up, who are the people from computing algorithms know that what is meant by the algorithmic speed up, which means that if I go on increasing the size of my input, what's the speed of computing, right? What is the time of convergence I get, okay? Fine. Normally we get, in classical computers, many algorithms are intractable. Intractable algorithms are those algorithms which means that if you are going with a large input size, right, you might not converge in years. Okay, you require some n years to converge the algorithm. Okay, an exponential speed up is that those algorithms which are intractable in the classical computing, which take n number of years. You will see, maybe 20 years. And some algorithms says that the time of the universe, right? You will be able to converge, right? And if it's exponential algorithm, exponential speed up means those algorithms can converge in minutes and seconds. Right? And that is the potential of quantum computer, and that's why everyone is now looking forward to the algorithms and to make the quantum systems so that we can really go into this level of computation. Okay? The third part, which is very important in the context of this particular conference is that if we can establish a quantum communication, if we have quantum sources, okay, quantum receivers, right, ideal setup, right, it is a perfect secured communication. Theoretically, if you can establish a quantum communication, like we will show some examples, right, you cannot decipher the data, right? And that is also a main attraction. And having said so, maybe the quantum communication requires much less resource than quantum computing. And it is indeed true that quantum communication, from the technology point of view, is a much stable domain than quantum computing. Because in quantum computing, you require a large number of qubits to at least give some sort of computing. But in quantum communication, you don't require that amount of qubits, right? Your messages are not of that, okay, that sizes, okay, right? Okay, fine, your keys are of not that sizes. So those are the good things what you can do in quantum communication, okay? Fine, and now I will give a little bit introduction of what is this quantum states. Okay, as I say that they are very exciting they are very exciting things to work out. Okay, when I started my PhD in a statistical institute, I was first exposed to these quantum states and then got further exposed when I went to Princeton for my postdoc. Right, and these are still exciting to me. It's not that when I'm not still excited by the quantum states. This still excites me. Okay. So we know that the classical computing, the premise of classical computing is that how we encode the data. Whatever data is there in the classical computing, ultimately it is represented by bits. Okay, and we know that bits, okay, a classical bit has two states, okay, two logical states. One is the state 0, which is normally considered as an electrically low voltage, right? And a state 1, which is implemented by an electrical a little bit higher voltage value than the low state. So we have a 0 and a 1 state, okay? But when we see the quantum state is a vector, okay? What is a vector means, okay? Some of you can say me, right? A vector means it has components, okay? Anyone who knows vector, we know that a vector means something which can be decomposed into multiple components. Yes or no, the students? Right? If I say that, hey, this is a scalar and this is a vector, what's the fundamental difference? Scalar means, right, it is that it is. What I offer you is that is the value and that is the only value what I can have. But if I say that I have a vector, it means that, hey, the first question comes that if it is a vector, sir, I can decompose it. Right? And that's the fundamental thing of a quantum state. So quantum state, instead of a definite value, quantum state is a vector. And when I get into vector, I'm not exposing those things. When I get the concept of vector, the people who are in machine learning, I think now many of the students and researchers are just getting into machine learning. When I say that, hey, this is a vector, the machine learning people get excited. Okay, because why? Because all our data in the machine learning, all our operations in the machine learning are basically multi-dimensional vector operations. So we can represent vectors in a better way in quantum because inherently they are vector, and that also excites us because we can map a machine learning operation, a kernel operation or a data into a quantum state most easily than a classical. Okay, so now if we see the top one, it's a vector. So obviously the vector can have two states which are 0 and 1 as that of a classical bit, but a vector can have different orientations, and these orientations means it has components across 0 and 1, and as it has a component across 0 and 1, this state is a superposition state. And this superposition state is pretty interesting state, and we cannot have a classical equivalence to that, and that makes the quantum computing so interesting, okay? If we explore this a little bit more, I'm not getting into the mathematics as it is a little bit, time is required for the audience to absorb, but just to get a view of this, this is a quantum state, okay? Which is idealized as a Bloch sphere, which is a unit radius sphere, which means that the radius of the sphere is 1, okay? And the quantum state is something which is coming from the origin of the sphere and touching the surface of the sphere, okay? Right? And that is the radial distance, which will always be 1, because ultimately, whatever is the component, the sum of the components will give to 1. And that's the analogy why this unit radius of the vector of the sphere. But the sphere is a three-dimensional space, okay? So we have a z-axis, which is the north pole, south pole, okay? We have an x-axis, and we have a y-axis, okay? Right? And this gives another thought process. Okay, so a vector, okay, which I show something psi, which is a quantum notation. Those who are a little bit oriented into the quantum physics, they know that this is a Ket notation. This Ket notation just distinguishes that, hey, this is not a classical state, but this is a quantum state. If I say that psi with a Ket notation, it means that psi is something I'm speaking about quantum. If I don't use the Ket notation, it means that psi is something, a particular variable in my classical domain, right? And that's the mathematically we try to differentiate, okay? So now psi is something which I show here, right? And you get another thing here now, okay? So psi can be measured across 3 axes now, okay? And that's the uncertainty in the quantum state, okay? So we have axis across z, we have axis across x, we have axis across y. Having said so, most of the time the measurements are across the z or the x. Why we don't use the measurement normally, okay? But this also gives you a handle that, hey, that means you give me a quantum vector, right? I measure it across the z-axis, and you measure it across the x-axis, you will get 2 different values. So what I need to know? I need to know 2 things now. I need to know the vector as well as the basis on which you are measuring. If I miss any one of them, I will not getting the same value what you are expecting. And that is being exploited mostly in quantum secret communication, right? And that is so exciting. And more you increase the number of bits, more and more the space enlarges into the tensor space, and more randomness increases. Right? From single qubit to 2 qubit to 3 qubit to 4 qubit, if you go on this, you will find more probable combinations can be oriented across the basis. 1 qubit can be on x, 1 qubit can be on z, 1 qubit can be on, again x, and then so combinations will come up. And so large number of combinations you can generate, and these all combinations will be properly decoded if we know the locations of the qubit vectors and the basis on which you have generated your data. Okay, right? So this is okay. So we say, what is a quantum operation then? What is the operation on the data? Can any student tell me, what do you mean by a computation on the data? Computation on the data means that we will take the data and we will do some basic operations. Basic operations means maybe some logical operations fundamentally and or not. Basic operations may be some arithmetic operations, adding, subtracting, okay, something multiplying. And this is computation fundamentally. Whatever large computation we do, ultimately we are doing mathematical and logical operations, because other than that your ALU cannot do anything. Ultimately you have to decompose it into that means the arithmetic or logical instructions which your processor can execute. And that is the computation on the data, okay? So now what we can do here, what we can do in quantum computing, okay? So in quantum computing, what is computation then? You have to change the value. What do you need to do? You need to just move the vector. So easy. And this gives you a very good motivation that how device and computing gets connected. In a classical computing, we are forcing a device which is in some state to actually raise its state value to lower its state value to 0 or raise its state value to 1, so that I can binary encode the 0 and 1, and I can do the combination. I can change the voltage value and I can again change the data. Okay? Here I have to change the vector, and these vectors are the quantum states of the matter. So automatically some quantum evolution the matter does. And if we can control the quantum evolution of the matter with a very low energy, I can compute. Is it yes or no? What is the computation energy? The amount of instruction we have to execute
to get our data get modified. Any computation algorithm is something which actually modifies our data, right? So now to modify the data, what we need to do? We need to just change the vector. We need to just change the orientation of the vector. And in some cases, you can do it by certain exciting the material itself. Okay, the quantum state, which is called a quantum evolution. So that quantum evolution is a very small energy process which can just change the vector. And without doing actual computation using a hardcore processor which is controlling the things, you can just use a field level controller which will just change the vector. And it has been proved obviously that this change of this computation is much, much sustainable. Though it is costly at this present point of time because we don't have the solid state quantum computing still very prominent. Okay, the quantum computers what we are having is mostly superconducting or ion trap computers, which requires a little bit lowering of the environmental energy. Okay, so minimum energy required is the plus and minus. Plus in the sense that if you are applying it, minus in the sense that the environment can also change it, and that can procure and that can generate certain noises. Okay, so let's go into the thought process of this. So what I said that a quantum vector can be decomposed because it is a superposition state, and this is an example of how the superposition state works. And this superposition of quantum state, if you go into the physics, is basically the wave property of matter, right? That means a particular quantum particle has a wave and particle duality, which means that obviously you can measure it to a particular value, which means it is a particular particle. But when it is a component, there are certain states which are not the perfect zero and perfect one. The vector is not oriented at the north pole or south pole of the z-axis. If it is oriented at the north pole and south pole of the z-axis, it becomes 0 and 1. But if it is not, then it becomes a wave, which means that it has certain spreading out. It has a spread out in 0, it has a spread out in 1. So that is what is being shown here. And that is being also this called Schrodinger's cat. Okay, Schrodinger's cat is a model where you don't know there is a probability of getting the cat out of the box, and when you get it out, it may be dead or alive, right? And there is always a 50% probability. Nobody can say that if I open the box whether the cat will be dead or alive, because the cat itself is on superposition. And if the probability of 0 and 1 are equal, then out of 100 experiments, 50 times you will measure the state as 0, and 50 times you will measure the state as 1, right? And that is quantum superposition, okay? And that I show here by this. And remember what are these alpha and beta? Alpha and beta are the amplitudes of 0 and 1. What does it mean? It means that what is the probability of, suppose I give you the vector psi, a quantum state psi. Okay, what is the probability that you measure the quantum state as 0? Probability is alpha square. What is the probability of a psi of getting measured as 1? Okay, the probability is beta square. So this alpha square, beta square, what I shoot as the amplitude of the components of the vector psi, and nothing but the probability, the square is nothing but the probability of getting the vector measured as either 0 and either 1. Okay, so these are the fundamental things you have to understand what is superposition, okay? Right? And this can be extended not only to single, I only try to focus on single qubit to make everyone understand, but you can extend it to multi-qubit. And if you go to multi-qubit, what do we have? What are 0 and 1 for a single qubit? Can you say me? 0 or 1 on the single qubit are the measurement basis. So a single qubit can generate values over all the bases, because single qubit has two bases, 0 and 1. Now it can generate the data for both 0 and for both 1. Now if I extend it to an n-qubit system, it will generate the data over 2 to the power n basis states. So imagine that using an n-qubit, you can generate a state which has 2 to the power n basis, and 2 to the power n basis will have their own amplitudes. And that is shown here, that if you have a if you have an n-qubit system, okay, if you have an n-qubit system, you will get 2 to the power n basis spread. So what it means excites for the data, right, the large data, okay, the big data, right? In big data, we are really bothered about how to represent this data because this is of a very large volume. Okay, because in the case of classical, the volume of the data and the resource is linear. Whereas in the case of quantum, an n-qubit system can represent a data spread over 2 to the power n basis states. So n resource can represent a 2 to the power n distinct data values. And that's what is the gain of superposition also, okay? And the next interesting part is entanglement, what I show here. Entanglement is another exciting part of the quantum states, okay? So what entanglement does is that if you see the first example, which is shown here, right? I show you an example of a 2-qubit system, right? Okay, I hope it works, huh? I don't know, okay. Okay, so it's a 2-qubit system I show here, right? Because it has basis state 0001, 1011. So basis state 0001, 1011 means it's a 2-qubit state, right? And this 2-qubit state, first example, can be easily decomposed into 2 independent qubit states, okay? So these 2 independent qubit states are the factors of the larger 2 qubit states. This is a common example. But there's an example which also grows with entanglement. So the entanglement example comes here. Suppose I give you this state which comes at the bottom, right? You have an amplitude for 0, 0, and 1, 1. So it means that it's a 2-qubit state. But it doesn't have amplitudes for 0, 1, and 1, 0, which means that the amplitudes for 0, 1, and 1, 0 are 0. And provided we can make this particular state, provided we can make it, obviously you can challenge me that, tell me that how we can make it. But provided we can make it, what we have, these are inseparable qubits. Now these qubits are inseparable because you cannot now factor these states into 2 independent qubit states. You cannot probably find A, B, C, D. You cannot find A, B, C, D, which converges to this expression. And this makes a very interesting phenomenon that we have a coupling between 2 qubit states, right? And you see there is a particular information also. So 0, 0, and 1, 1. So 0 comes from first qubit, and the next 0 comes from the second qubit. Similarly, for the 1, 1 state, 1 comes from the first qubit, and the second one comes from the second qubit. Now, if we measure this quantum state, now the measurement is a very important thing in quantum. So quantum doesn't mean that you have to only initialize a quantum system and you have to do quantum transform. So 3 important things in quantum system is that initialize, encode in the quantum system. Second is operate, transform on the quantum system by the quantum operations. And third one is the measure. So measurement of a quantum system can only be done on one of its bases. You cannot do so. So if you are a 2-qubit system, you can only measure the quantum state across 0, 0, 0, 1, 1, 0, 1, 1. Because these are the 4 bases you can do. So any one basis, against any one basis you have to measure. So now, if you measure this particular quantum state, we know that the first qubit is 0, obviously means the second qubit is also 0. And if the first qubit is 1, the second qubit is also 1, which means that inherently, if we measure the first qubit only, second qubit is automatically known to us. And this, if we extend it for the large number of qubits, it's a difficult thing how to entangle large number of qubits, but probably if we can do, it's a multi-party communication. Because a sender entangles a qubit, right, and sends the entangled qubit, to the other party, right, and whatever measurement sender does, the other party can retrieve it. And that is the process of quantum teleportation, what I will explain in my next subsequent discussion, So these are the 2 exciting phenomena what we have in the quantum, One is the superposition, and one is the entanglement, And this is also a very interesting thing, no cloning theorem, which actually is called the preserving or adds the security to the quantum system. Okay, so no cloning theorem tells that if we have an unknown quantum state psi, there is no operation possible where we can produce another copy of psi. We cannot copy the psi, and that is the no cloning theorem. Right? And this also helps a lot in the security applications. Okay? You cannot copy an unknown quantum state. In a classical state, you can do the shift registers. You have registers operation by which you can transfer a quantum classical state to another classical register by some sort of shift operations or transfer operations. But in quantum you cannot do. Because if you have to do in quantum, the logic which comes upon is that this measurement, psi and phi, is equal to psi and phi square up. And this is only possible when psi and phi are same or psi and phi are orthogonal. So if psi and phi are same and psi and phi are orthogonal, those are not a general quantum state. A general quantum state is a superposed state, okay, which contains both the orthogonal values. It has a component equals 0, it has a component equals 1. A general state cannot be 0 or 1. So this can only be copied if you know the quantum state is only 0 or quantum state is only 1. But if a quantum state is a generalized quantum state, alpha 0 plus beta 1, you cannot copy it because then you violate the quantum principle. And you cannot violate the quantum principle, so no cloning theorem is so important, okay? Then I go to some of the things, the exciting things. Okay, I tell it promises and hype, because though I am a very passionate quantum computer researcher, it doesn't mean that I will just push everything to quantum. Everything is good in quantum, right? Like any researcher in his domain will say that, oh, this is my domain of research and everything is good here. It's not always like that, right? It's promises and hype. Means that there are a lot of promises has been generated, right? If you see the things which are done by IBM, which are done by Google, which are done by NVIDIA, okay, all are very exciting. Okay, these are all recent papers and literatures. Okay, but having said so, it needs to be understood or needs to be experimented that what is the scale in which we can do it. It shows the promises with a few handful of qubits. Can we take it to a larger number of qubits? Can we make a large-scale quantum computer? Right? And so for that, a lot of things needs to be done. Obviously, that is the research. That is the technological research that we overcome the challenge. And the good point is that every year we are increasing towards that. If you see the IBM progress, okay, when I started quantum computing in ISI, no IBM was there. When I was in Princeton, no IBM was there. When I came back to India, IBM started in 2012 or 13, right? Right? And now not only IBM, there are Rigetti, okay? There are Delft, okay? There are CQT in NUS, okay? There are Tokyo University, right? They have all their own quantum computer. Most of the strong universities have their own quantum computers, okay? Right? So that was, and also the companies like IBM, like Rigetti, like it's a Honeywell, okay? All of them have the quantum computers, okay? So it's very exciting, but we have to see the full stack in quantum, okay? Last part that all the things I've discussed, this is just a summary, okay? That whatever I have said up to now, it's just a summary that, hey, if I try to compare between classical and quantum, okay, one against the another, where I gain, where I lose. Obviously, I gain in terms of computing capacity, okay? Because exponential computing capacity, n qubit give you 2 to the power n data space, which is not possible in classical, right? If you have to increase your register from 8 to 16, you have to add 8 bits in your memory, you have to add 8 bits in your data path, you have to make your ALU from 8 to 16. So everywhere you have to go on adding 8, 8, 8. From 16 to 32, again the same thing, 16, 16, 16, go to add. So it's a linear. So the resource is to computing power is linear, whereas the resources to computing power in quantum is exponential. So your gain is pretty good, okay? Last 2 points are pretty important, okay? I will get it. So the error and stability. So as it is a quantum vector, it's not a it's not a well-defined stable state, okay? So quantum vector is a fragile system, is a fragile state. So now a little perturbations in the environment can change the vector. So now you will question that whether it is a gate computation, whether I have done it, or the environment has done it. If environment does it, then you have shifted the state from your, that means what state you are trying to generate to your quantum, to your computation, the state has shifted due to environmental perturbations. And those shiftings are basically, in terms of data, is called the errors. If we shift your data value from what is required, it is the error we generate. And this error is pretty obvious in quantum because the quantum vector orientation can get shifted due to the environmental noise. So now the environmental noise needs to be very well controlled, or you need to have an error correction scheme which can correct this error. So we have very good classical error correction schemes, but those error correction schemes are still a little bit constrained in the quantum domain because all error correction schemes require redundant bits. And as the number of qubits are pretty less in quantum, you are not at that point that you can just take bits, for error encoding, but not for computing. So now, and the last one is the suitability. It is not like that, you just blindfold me and tell that anything we put to quantum computer will work. It's not like that. It's called the quantumness of your problem. It is not that just like every algorithm gets speed up in a parallel computer, it's the same here also, right? You have to understand that which functions of your algorithm will get a real speed up. So we have to do analysis of the algorithm, of the function, and the quantum will be most generally, it will be an accelerator, which means that it will accelerate a section of your application, of your function, of your code, So that's the way we are, and that's the way all the things are coming up in the cloud service. So quantum comes in a cloud service in a sense that you can always get attached to the resource for the specific threads of computing which you are trying to push. So you have to analyze well that which threads in your computing will be good to go for the quantum system, Right, and this is what I said, that we are moving towards, from the very, very nascent state to the mature state in the quantum, right? And once we reach there, we will say something as fault-tolerant quantum computing, which is theoretically there, but we cannot implement that because fault-tolerant quantum computing requires a large amount of qubits, and we don't have that. So the present era of quantum computing is called NISQ, noise intermediate state of quantum computing, NISQ state. So we are gradually progressing, and you see that somewhere if we hit over 10,000 qubits, we are pretty well in the fault-tolerant quantum computing, which is a pretty stable quantum computing, which will get much low noise. And if you are going 100,000 qubits, we are really doing good, and we will imagine if we have 100,000 qubits. Why I'm telling this? Imagine you have 100,000 qubits, Fine. Our classical computer will not exist. Why? There is already an alarm. I'll not name the companies. One company was predominant building the processors for the last 60 years. So I'm not naming the company because both are my very good friends, One company built the processor over the last 60 years. And when we were students, when we were researchers, we thought that was so good, so big company, Another company came for the last 25 years. They changed the pipeline, right? As the CTO says, when we met, he said that we changed the pipeline, and they changed the pipeline of computing, and now nobody cares of that part of the computing. People cares about that part of the computing which this new generation computing came up. Because the applications are so dynamic, applications are so large that you need to focus on that part of computing rather than the computing which is already we all know how it works. So we probably don't know that once we reach 100,000 qubits, your computing in that quantum level will be so enormous, so much great, it will just leave this computing. Okay, right? And that is why everyone is making this quantum computer thing strengthen and strengthen, right? And we have to pick it up. Okay, it's a little bit core technical thing in quantum computing because you need to, for the students, for the researchers, okay? Okay, that means everything, that means the thing is hard, but you know that if you can conquer the hard things, right, those are really which matters. Okay, if you conquer the, okay, that means the smaller challenges, it doesn't matter much, okay, to anyone, right? So if you are master of quantum computing, right, it is obviously you can contribute in this scale, in this particular paradigm, okay? Okay, let's move on. I will just give a little bit, I will just skip a bit because how much time I left, anyone from the organizers? 20 minutes? 30 minutes? Huh? I will take my time. Okay, so good, okay. So I am just squeezing it a bit now. So we have studied the bits and qubits, and now I am getting into the operations. Our computation knowledge tells us that operation means are gates. The fundamental operation in a logic system is the gate operations. And let us try to see what are the gate operations vis-a-vis the classical and quantum, okay? So I show the classical on the right and the quantum on the left. So classical means, we know, and, not, XOR, and all these things, okay? In quantum, what is this? Rotation gates. When I stuck in my initial study of my PhD, 2004, 2005, I was surprised to know that what is rotation gates? We know logic gates. Why rotation gates? Because, as I showed, the vector is a quantum state vector, and quantum state vector moves in the three-dimensional space. And the movement is rotation, right? Unless you cannot move the vector because the dimension is same, so you cannot shrink the vector. You can only change the state by moving the vector. And that's why the fundamental operations are rotation vectors. And rotations can be done in any of the three axes, x, y, and z. So we have the fundamental quantum operators or gates, which are Rx, Ry, and Rz, which are also called the Pauli operators. Okay, right? The second one, entangled gates. Entangled gates are nothing but the gates which operates on more than one qubit. Normally, in the technology side, you don't have, still now, you don't have gates larger than 2 qubits. You have gates 1 qubit and you have get 2 qubits. And it is sufficiently shown that if you have 1 qubit and 2 qubit operations, you can execute an algorithm. Okay? And that's why you know that the fundamental quantum machines started with studying 1 qubit and 2 qubit operations. Because if you perfectly know 1 qubit and 2 qubit operations in a quantum system, right, you can analyze any large-scale operation in a quantum system because ultimately you have to decompose or synthesize your high-level logic circuit into 1 qubit and 2 qubit quantum primitive operations. Okay? Now we will I will show a little bit that what are these 1 qubit and 2 qubit operations in the concept of the states, okay? So you see that what I have done here, so this particular quantum state, which I show here, is exactly at the north pole of which is the z-axis, one end of the z-axis. And that we label as state 0, pure 0. It doesn't, because it has 0 component is 1, and 1 component is perfectly 0, because it's, okay, just the orthogonal. You cannot have a component and orthogonal, right? But a rotation gate will bring the state somewhere here on the Bloch sphere. And once we do that, it becomes a component across 0 and 1. It changes the vector. So that is so important in the case of quantum. And now I go on doing this, playing this game, okay? So now to the students and researchers, okay? Initially people thought that, hey, quantum algorithm is something that we will have a classical algorithm and we have some sort of automatic parser which will make a classical algorithm to quantum algorithm. So it's not like that. So if you have to work on quantum algorithm, because the computation is different, the states are different, the way we measure is different, so we have to completely come out of the thought process and we have to completely think that, hey, modification of the data means where is my state vector in my basis state, right? And what are the operations I need to do to change the, change the basis, to change my quantum vector so that I can have different values across the basis, which is the computation. So I show that what are the things you can do. Across Rx and Ry and Rz, these are the gates which actually move across X, across Y, across Z axis and change the quantum vector. And every change will give you a different value on measuring, okay? So we talk about distributions, okay? Now I come a little bit on the motivating the students and researchers in machine learning. What is machine learning? Anyone? Any student wants to volunteer? What is a machine learning? In a very small, in a very top level. Machine learning, what I feel, is understanding distributions. Machine learning is nothing but understanding distributions. If you can generate distributions which maps the domain, then you have learned the domain. Yes or no? Yes? Right? And the thing is that there are two things of it. One is supervised, one is unsupervised, right? In supervised, you generate distributions by learning some samples of the distribution. Right? In unsupervised, you just qualify the distribution, but don't tell anything about it. And generative AI is generating samples out of distributions. Okay, so three components of AI and ML are nothing but understanding distributions, okay? And what quantum can do? Quantum can generate distributions according to your will. And that's the power, if you can do it. If you can do it, at your will distribution generation is quantum, right? And this, what I show, is a single qubit distribution. So a single qubit equally superposed state will generate a distribution which is 50% 0, 50% 1. So you have two classes, 0 and 1, and I have equal probability. But I can bias it a bit. I don't start from that vector. I start from this vector. And I again measure it. I get a different distribution. Okay? Right? I will come to this pretty soon. Okay, so now these distributions are the key points of the quantum operations. And you can probably, I'm not discussing machine learning. This is my very close topic, quantum machine learning, but I cannot cover the quantum machine learning and communication in a single lecture. So I thought I will keep it for some other discussion. So I've just excited you that you can now start thinking that, okay, professor has said that distributions, okay, random distributions, quantum systems, how I can exploit this in machine learning. That's a thought for all of you. Okay, now I go to the focus part. Okay, so ended up here. So obviously you need to verify your quantum algorithm. Okay, so verifying the quantum algorithm means you have to represent your algorithm in terms of quantum operations. And this is a platform called Qiskit, okay, of IBM, which represents a quantum algorithm in terms of the quantum gate operations, starting from the qubit descriptions, then the quantum gate operations, and then the measurement. And you can find that whether these quantum operations will lead to the quantum values what you expected as a result of your algorithm. Again, not getting into details of everything, but you can easily find out in reference. This is a very standard platform, and you can try out your algorithm, map it to quantum circuits, put it into an IBM Qiskit machine, or the other like NVIDIA CUDA Quantum, and you can get the output. Okay. Fine. Now I am coming to the last part of my lecture, which is the quantum communication. Okay. So I set this up to all of you because you need to. That means whenever I give a quantum computing lecture, I don't know that where the baseline of the participants are. So I try to just motivate them in the initial thought process of the quantum. Okay. So now we know that classical algorithms are there. Okay. We have the asymmetric cryptography and we have the symmetric cryptography. Which is better? Asymmetric and symmetric. Which requires less resources? Asymmetric, how many? Less resources. Asymmetric, raise your hands. Students. Asymmetric requires more resources or symmetric? Asymmetric requires more resources because asymmetric you need to have work with two keys. Okay, private key, public key, right? You encrypt with the public key of your receiver and the receiver decrypts it with its own private key, right? And you have to make a sort of generating the key, okay, is a process, okay? Yeah, so I'm just skipping it. So symmetric cryptography is always better because you have only one key, right? We encrypted the key, and if the receiver has the same key, a receiver can decrypt it. But what is the challenge in symmetric cryptography? Challenge is that, hey, how I will share this key? There is no channel. There is no channel where I can share a key, okay, where I can share a secret key. Now, this problem, if it is solved, then we can do the classical cryptography very easily in a very low resource environment, low cost environment, okay? So let's see how we do it. I will just skipping a bit on this. So this is the QKD, quantum key distribution. So we need to have a key distribution. Okay, key need to be distributed between the source, right, and the receiver, but there will be no chance of the intermediary, adversary, okay, which is the Eve, will not able to get that, okay? So this is the technique called QKD, quantum key distribution, where we use a quantum phenomenon to distribute the key between the two parties, and once the key is distributed, right, they can go with the symmetric key cryptography, okay? Right, and that is the process how we do. So we require something, a device called QKD to enable that, okay? Okay, right, and this is the process. So what we do here is that we first set up a quantum channel between a sender and a receiver, right, and they settle down the key, and once the key is settled down, then they can go on using that public channel to actually communicate, okay, because the key is already being transferred, okay? Now the problems are that what are the things a Eve can do when I am communicating the key in the quantum channel? Okay, that is that challenge. If we can take care, then I think we are done. We are good. Okay. So I'm just actually there are certain things which we have to take care. QKD is one of the premises of quantum cryptography because key sharing is there. Okay. Right, and no cloning theorem is also there. We have to take care. Right, you cannot copy an unknown quantum state, okay? Having these two, let's just try to summarize the protocol in a little bit, visualize the protocol a little bit way, okay? So what I show here is Alice is a sender, and Bob is a receiver, okay? What is done here is that I've already said the basis. Obviously, this is a photonic experiment. This is a photonic experiment, right, which is being done. Okay, so what do? We go with a ideally single photon, but again, I'm not a photonic expert. I don't know how challenging it is, but let us go for the ideal case. So ideally, it is a single photon. So single photon, okay, goes, okay, right, and each single photon is sent from the Alice, okay. Its polarization basis is being randomized. So first photon I send with a normal basis of Z. Second photon I send it on X basis. Third photon on something, Z, again X. So there is a combination. So you see this random movement is a combination of a randomization between X and Z basis. Okay? Now because a particular photon state measured across X and measured across Z basis will be different. Okay, now what receiver will do? Receiver will not know that, okay, what bases have been sent randomly by Alice. But Bob will also try to make it the best possible way to match it. And in order to doing this, he will match in some of the cases, he will fail in some of the cases. What will happen when he matches? When he matches, he will receive the state with a very high amplitude. When Bob fails to match its polarization, okay, because this is a grating, polarization grating, right? And this is a polarizer. Okay, so you have to orient the grating in terms of polarizer, okay? So if the orientation fails, Bob will get a very low value. Okay? Right? So Bob will get a very low value on those cases where the Bob's orientation is not exactly the same as the Alice orientation was. And then what will happen is that Alice will call Bob. Hey, Bob, let me know that which number of photons you received properly. Bob will say, hey, I received 1, I received 5, I received 6, I received 9, I received 10, something like that. Okay? Now, if a third party, let us consider that a third party can able to trap any one of this. First of all, if a third party able to trap this line, what will happen? Any quantum injection will lead to law interference, and Bob will immediately know that the error has increased. So the error has increased means he will stop that. He will stop the communication, right? And he will try to use another quantum channel. So this is a very important thing. In classical, what is done, attack is being done, and then we can recognize by the effect of the attack. In a quantum channel, if we try to attack it, if we try to disturb a quantum state, anybody who is the other side will know that there is an increase in error, and you can immediately stop or change the channel. So this is the immediate response you can do in a quantum communication. This is the first thing, okay? So any attack in the quantum channel that ideally will be taken care of. And now suppose Alice is calling Bob and telling, and Bob is responding that, okay, 1 I got perfectly, 4 I got perfectly, 7 I got perfectly. If this answer goes to the Eve, what happens? Eve only knows that, okay, 1, 5, 6, he doesn't know the data, what will be transferred, or the basis. So it's impossible for anyone to decode that what is exactly going on between Alice and Bob. Okay, only Eve will respond, okay, 1 I have received properly, 5 I have received properly, 7 I have received properly, 9 I have received properly. If this is decoded by an Eve, it's not possible. Only Alice and Bob can understand that what is going on between them. And what then done, then Alice understands that what are the orientations Bob have matched correctly, and then they settles the key on those orientations. And then he will say that, hey, now my orientations are exactly in the order what you measured. 1, 7, 8, 12, 15. I will send in that orientations and you measure it, get it done. And then the Alice and Bob will share a key. And the key is nothing but the randomization of the basis. Okay, so this is, I'm just skipping it a bit. Okay, there are certain issues. We are doing a work with CDAC here. This is very important, that though we tell that everything is quantum, ideal quantum, but ideal quantum is very, very difficult. So what will happen in the QKD if there are some non-ideal quantum? I'm just giving you a research thought. If you want to connect with us, it's fine. We will be very happy. So we are trying to work on the different noises and also side channel scenarios for a QKD. And this is very important. DRDO also visited my lab recently. So it's very important for DRDO, CDAC, that either in the business applications or in defense applications, QKD are coming up, right? And so we have to understand that what happens here, okay? Okay, the second thing is that, okay, quantum teleportation. Again, I think I have very less amount of time, so I will just close within 5 minutes, sir. It's okay? 5 minutes, okay. Oh, 10 minutes, good. Okay, so quantum teleportation is something. So why I require quantum teleportation? I have already said that quantum no cloning. So would I not be able to transfer a copy, a state from A to B? Because it's no cloning. So how A to B data will be transferred? Because B wants the same data as A has. So how we can do that? Okay? One is that we can send a QKD and establish a classical channel so that A can communicate a B. Now, in a quantum system itself, because we have different quantum subsystems, and quantum communication can be in some point of time through quantum channel. It's costly, so we are not getting into quantum channel. We are trying to distribute the key into the quantum channel, and we are using a classical channel. But suppose there is an infrastructure requirement that I want to make up a quantum channel, or I have to communicate between two subsystems of a quantum system. How do I communicate? Because I cannot copy. No cloning. So the way I can do is a little bit step which is called teleportation. Teleportation is the process by which a quantum state in A can be transferred to B. Okay, this can be done in the quantum system itself, and this can be done for a true quantum communication itself. Okay, the basic algorithm, okay, so the figure is something like this. Okay, again I show it on photon because it's communication side. In the quantum communication side, the photonic states are the states which we use for quantum communication. So the scheme is that we use the photon state, but we have to generate something called EPR pair. EPR pair are basically the Bell states, okay, which are entangled. So we have to create an entangled state, and a part of the entangled state will go to A, and a part of the entangled state will go to B. And we will see now, with this, a little bit cost. Obviously, you guys say, as I said, it's so costly. Yeah, it's costly, but you are doing quantum, right? And you are maintaining a security. You have to, that means invest on that, okay? So there are a lot of steps out there. That this slide will be with all of you. You will go through, but just to summarize it, what happens is that, okay, that means I am a, okay, Alice, okay? So there is an EPR pair generator called a Bell state generator, which is the service provider. So what is the business? So business will be here, okay? We will have Bell state service provider, and people have already started this. I'm not telling the companies. People have already started this, that I will give you a Bell pair. So take my Bell pair, okay? So there will be some service of the Bell pair, and the Bell pair will be going to A and B in the sense that this is an entangled, so a part will go to A and part will be with B. Okay, so what will happen here is that the Alice A will do an operation, certain operation, okay? So A already has a quantum message, okay, which needs to go to B. So now with this entangled Bell pair, he will do a certain operation with the message. Actually what he will do, he will project his message on the Bell state. And he will get a measurement. Alice will get a measurement. And the measurement is a classical value. Once we measure a quantum state, it becomes a classical value. So try to again remember that what it does actually is that the message, the quantum message of Alice is measured against the Bell state, what is being generated by the EPR pair. And the measurement is a classical value. Now this classical value can be communicated to the Bob. And Bob, with this classical measured value of Alice and a part of this Bell pair, it can do a quantum operation at the basis, at the Bob side, and it can regenerate the message which was being at the Alice side. So there are 3 steps here. Step 1, generate the Bell pair. Step 2, measure the Alice message against the Bell pair, get the classical value, push it to Bob. Bob, take the classical value from the Alice, okay, take the pair of the Bell, and do a quantum operation and retrieve the state. Okay, it's so easy to say, it's so number of steps. So there are basically 3-4 steps you need to do, and this is explained here exactly. Prepare the message, entanglement is required, okay, generate the EPR pair, okay, then actually one part will go to Alice, one part will go to Bob, okay, do the Bell measurement at the Alice side, then this measurement will go to the Bob side. Bob will do certain quantum operations based on what he receives, and she can exactly generate the quantum state. Okay, so this is what is this, and you can try out this entanglement circuit in all the things. Okay, are there. Okay, this is the part that this is something which is just a sort of illustration. Okay, nothing much to discuss. Okay, there is a phenomenal paper I was discussing with professor yesterday, right? And we are discussing, there's a group from Italy who has already given the blueprint of quantum internet, right? And we are really working with CDAC and DRDO to try to frame it up, right? And anybody wants to have a thought or wants to connect, I will be very happy. So these are some of the thought process of quantum. So if we so these are okay, these are A to B, B to C, but a quantum network means multi-party communication. And for multi-party communication, we require security, we require channels, and we require what? We require repeaters. It is not that you can just send from A to B a long-haul communication by one communication channel. It will not be possible. You don't have so much of energy, right? You don't have energy to do that, okay? Though people have tried to do using laser, that means a communication between the Earth to that means from the satellite to the Earth. Things are coming up, right? But we have to make it in a normal network, okay? So these are the things what you need to do. So you need to have so each of the nodes, this is the model. I'm just proposing a model of quantum network, what it will be. Quantum network will have quantum nodes, and network means connection of nodes. So we will have nodes which will communicate, and there will be a communication link. Each of the nodes we can assume in terms of quantum bits, qubits will be there. Some qubits will be actually communicated, some qubit information communicated, and some qubit information will require in the node itself to prepare the quantum state and to do some other work, okay? And there will be some quantum operations we need to do. Okay, because we are from computer science, I am not a communication, okay, I'm not a communication expert, okay, like all of you. I am more a computing expert. So in computer science, the good point is that we can abstract anything, right? And the graph is most of the important thing. So we take a node in this point of view, and then what we do, we try to define the certain nodes as quantum computing nodes and certain nodes as quantum repeater nodes, because there will be repeaters. And then we try to extend what will happen in the different stack operations. So we know that quantum control and quantum key management are there. Quantum physical layer is also there. So these three are very well settled technologies. Okay, now the top technologies like transport, okay, application, this needs to be connected with this particular protocols, right? And that is a good amount of challenge we all have, okay? So these are the most probably thought process. It's a thought process. I'm not telling it's a done thought process we can do, okay? So I think you can go on this. A lot of applications are there. If we are there, okay, blind quantum computing is something like homomorphic encryption. Homomorphic encryption is so good, but in the classical it's very costly. Those who have worked on homomorphic encryption, nobody does homomorphic encryption. It's all partial homomorphic. But probably, if we have quantum, we can probably get into homomorphic computation very quickly, because we can do blind computation. Blind computation is very exactly the similar what we do homomorphic. And this is very interest to the business community. They are trying to, we had a meeting with HCL, right, and IBM, right, and they both requested me present something on this particular part, which is called blind quantum computing. Okay, that is, again, I'm not presenting that due to limitation of time, but this is a very interesting thing, okay, we can do. Okay, so I'm just skipping. There are some example, good established quantum communication networks, like which happens in Geneva, Swiss. It's established by CERN. Okay, yeah, that means I was also a fellow of CERN in 2015. I was very lucky to be there. Okay, so this is the Tokyo QKD, which is already being implemented and available in the public domain. But many of the things are there which are in a very closed domain, and many of the organizations are doing it. Okay, right? A lot of applications are there. I'm just moving, and this is the space where we have to see. So it is not that what I said today is quantum, but don't think that it is all quantum. It will be classical quantum hybrid in communication, in computing, and that is the way we have to think, and that is the way we have to scale our research in both the domains. The interface is more important. Okay, a lot of things are there. I'm against quantum memory, fault tolerant, all the things are there, okay? Challenges, yeah, I'm just closing. Challenges are hardware limitations. Still, we are not in sufficient amount of qubits. Errors are high, okay? It's not scalable at that scale, okay? Hybrid quantum classical approaches, still classical and quantum are partitioned. We have to have a more joint activity. Okay, classical can exploit quantum and quantum can exploit classical. We have to find the way how we can do it, okay? Right, and then data encoding and ethical and security considerations. As a powerful tool, we have to do the ethical considerations, okay? Right, and this is a group which we are doing with a lot of corporate support, and a lot of institutes are there, international institutes are there, which are working with us. Okay, these are my good students. Some of them already graduated and got into good positions in industry and research, okay? Yeah, so thank you all. If any questions, I will be fine.
Thank you very much, sir, for this enlightening talk. I think this quantum technology is one area which is globally very popular, and a lot of people, experts are working. And in India, with the quantum mission launched by Government of India, so we are definitely trying to take a lead in this particular technology. And with such experts working with us so closely, I'm sure that this will be a platform from where a lot of innovative ideas, a lot of research problems, and many new research groups will be created. And this is the outcome that we expect in terms of the success of a conference and this particular tutorial. Thank you very much, sir, for taking us through this entire details of quantum technology. May I request Dean Research, Dr. Bhuvnesh Kumar, to please felicitate our speaker. Yeah, in the meantime, if you have any questions, any students, any researchers, participants, you can take the question. वापस लीजिए। चलिए, take it back.
Within the time.
और take it back, we'll pack it. We'll begin the next session at 11 a.m. All the students and faculties are requested to be seated here, right? All the class coordinators, please ensure that students are seated here. I'll request the guests and registered participants to assemble outside the auditorium for networking and interaction with each other. We'll begin the next session at 11 a.m. sharp. Thank you. Thank you very much. With the theme of conference being AI and 6G Nexus, I think this is something quite relevant and important, where we are trying to understand that how this artificial intelligence is integrating with the wireless communication, the advancements that we see with the 5G and 6G coming up, how we are really taking these new challenges of communication system with the help of AI, machine learning, and deep learning. So I'm sure that this particular tutorial is going to be highly knowledgeable, and it will give us many, many new areas where we can work further. I request you to take over, please.
Chains, Bunty.
माउस था इसमें नहीं वैसे तो तीर वर्ग है तो उसके माउस को बोल देना माउस ले कहाँ पे हेलो माउस किधर लेफ्ट साइड करो भाई लेफ्ट साइड के लिए बोल रहा है लो एक बार बात करो हेलो
किस पे आ गए?
Hello, everyone. First of all, I wanted to thank the organizer of WPMC for letting us do this tutorial today. So in this tutorial, Professor Oriol and me, we are going to be talking about reinforcement learning for beyond 5G radio access networks. And we will cover, apart from giving an overview of reinforcement learning and machine learning in general, we also will deep into all the process from the design to the implementation of this kind of algorithms for the radio access network. We both are researchers in the mobile communication research group in UPC in Barcelona, Spain. So in this slide, you can see the different points that we are going to cover during this presentation. So first, I will give an overview of what is the role of artificial intelligence in 5G and beyond. Also, another overview of machine learning algorithms. And then I will cover what is the applicability of reinforcement learning for the RAN. Then we will move to explain what is all the process that we need to do from the design to the deployment of this kind of solutions in the production. And finally, I will give a use case example for a problem that is for capacity sharing in RAN slicing. And also we will cover different research contexts where we have applied this solution and all the concepts. And finally, we will conclude. So let's start with what is the role of artificial intelligence in 5G and beyond. So 5G was initially conceived to provide a wide range of services that have heterogeneous requirements. I'm sure you have already seen this triangle here where we have the three main types of services that were devised for 5G. One is the enhanced mobile broadband services, where we have high data rates, area traffic capacity, and spectrum efficiency. Also, we have massive machine-type communications, where we have a lot of devices that need to be connected with a high density, high energy efficiency. And then the third type of service envisaged for 5G is the ultra-reliable and ultra-low latency services, which require really low latency, high reliability, etc. So in order to address and to provide all these services that were envisaged for 5G, new radio 5G architecture was created to be able to fulfill these services and to satisfy their demands. These included new features. From an architecture perspective, these included features such as network slicing, or the split of the G-node-B network functions. And also from a radio access perspective, this included high frequency ranges, flexible numerologies, and also enhanced multi-antenna transmission. Overall, all these new features, here I just included some. At the end, this increased the complexity to manage this 5G network. So we need tools that allow us to be able to deal with this high complexity. So artificial intelligence and machine learning were devised and identified as a key enablers for this transformation to a more intelligent and automated network. So now we are already looking forward to 6G. In 6G, it is envisaged that it will provide even more stringent REST service requirements. So for here, I included some of the envisaged services for 6Gs with non-terrestrial communications, extended reality, autonomous driving, and V2X, etc. So this will involve even more complexity to be able to meet these more stringent requirements. So the 6G network, for sure, it will be an AI native approach. It will be AI native, where AI will be supporting 6G, but 6G will be also supporting AI services for the final user. The standardization bodies are working on the integration of artificial intelligence in networks. So here you can see three bodies that are working on this. First one is the Open Run, that it proposes an architecture that is built on a virtualized radio access network, and that with open hardware, and that it uses the cloud. And this architecture embeds artificial intelligence. It has different functionalities that allow supporting AI, and also includes different open interfaces that allows to be able to leverage this AI for the management of the radio access network. Also, 3GPP has identified the AI as a functionality. Sorry. So as I was mentioning, AI, the standardization bodies are working on integrating this AI. So in 3GPP, as I was telling you, they have different work items and studying items that they are working on how to use artificial intelligence for the management of the network. This is related to the last releases. So these technical reports and working items are focusing on how to deal with the workflow of AI and machine learning, and also self-organizing networks are devised as functional candidates to incorporate artificial intelligence and machine learning. Also, in the ITUT, it specifies an architectural framework for machine learning in networks in general, that it also covers 5G. They propose a high-level architecture where we have different requirements for machine learning solutions and different components that are related to all the machine learning pipeline from the collection of data, the training of machine learning solutions and its deployment, and it includes functionalities for the management and also the orchestration of these functions. So, having addressed this need for networks to integrate artificial intelligence to be able to be managed and to be able to deal with all this complexity, now let's move to have a brief overview of what is machine learning and what machine learning types we can use in networks. So, in general, machine learning is a type of artificial intelligence that allows computers to learn a solution without being specifically programmed and based on data. So we have different types of machine learning that you more or less know, but let me revise this. So we would have supervised learning, where what we learn is a mapping function and we learn this from labeled data that is provided by external supervisor in the form of pairs of input and desired outputs. In supervised learning, we usually use labeled data. Then we have unsupervised learning, that here what we learn is a particular pattern or hidden structure on labeled data. And a combination of these two, or cooperation of these two types of machine learning algorithms would be semi-supervised learning, that here what we have is a small portion of labeled data and lots of unlabeled data, and then we, thanks to the using unsupervised learning into these unlabeled data, we can pre-label the unlabeled data and then train a predictive model. So this is quite useful when we have just a small amount of unlabeled of labeled data, which is a common, which will be a common case. Then we have reinforcement learning, that will be the focus on this presentation. That here what we learn is a long-term objective function that is learned through the dynamic interaction of an agent with an environment. This is usually used to learn decision-making policies, and this will be quite useful for radio access network problems. Although, so also, apart from this type of these three or four types of machine learning, recently there has been a tremendous growth of other types of machine learning that are complementary to supervised, unsupervised, and reinforcement learning. These are the neural networks that try to model the connections that we have in the human brain. So here we have different node layers. We have an input layer, one or several hidden layers, and an output layer that are interconnected and allow us to approximate the connections that we have from the inputs to the outputs. I have different types of neural networks like multi-layer perceptron, convolutional neural networks, etc. And also the latest advancements in neural network would be deep learning, where instead of having just one hidden layer, we can have several hidden layers, which allows to deal with more complex problems. So neural networks and deep learning can be applied and can be leveraged for the rest of supervised and reinforcement learning. So this is quite relevant for the application of this kind of machine learning problems to more complex problems that we have. And also, although we won't focus on this, I couldn't miss to mention generative AI, which has seen a really huge growth during the last 2 years, I would say. That is a subset of deep learning models that allow to generate content like text, images, or code, or even on data. So we've given a provided output, and here, for instance, we could have a GPT models that use transformers. So this is something that, although we won't focus on during this tutorial, for sure it will have a huge impact also for networks and for the society in general. So as I said, in this presentation, we will focus on reinforcement learning, since reinforcement learning allows to deal with decision-making problems and allows to learn a decision-making policy to make control actions. So let me just show you what are the main elements in reinforcement learning. So reinforcement learning, we will have a reinforcement learning agent, that is the learner, is the one that learns. Then this reinforcement learning agent is based on a policy that defines what is the agent behavior. And this is a function that maps what are for a given state that we can get from the environment, what action will this agent take. Then this is the state of the agent. What it does is that it captures what is the situation that we have in a given environment. The action is the action that makes the agent that is sent to the environment, and then according to this action, the agent will receive a reward assessing how good or how bad was the previous sent action for the previous state. So based on this, the reinforcement learning agent can update the policy and make it and optimize it. This optimization is made by a reinforcement learning algorithm that there are several, as you will see in the following slides. And this algorithm, what it does is that it takes all the experience of the states, the actions, and the rewards, and optimizes the policy so that the maximum reward is achieved by the policy in the long run. While this can be approached in different ways, here I wanted to highlight that many reinforcement learning algorithms are based on the value function that predicts what will be the expected reward for when we take an action and we are in a given state. In order to this process that we have of obtaining the rewards, taking actions and obtaining rewards, this is called the training process of a reinforcement learning algorithm. So this reinforcement learning agent will be dynamically interacting with the environment until the optimal policy is achieved, or suboptimal policy. So here I wanted to also to say that during this training process, usually the policy that is considered is an epsilon greedy policy that with a certain probability, with a probability epsilon, selects a random action so that we can explore new states and new actions in the environment, and with a probability 1 minus epsilon, we exploit the current knowledge that we have for our policy, and we obtain actions according to the policy that we are learning. During this training process, we always have an exploration phase and an exploitation phase then. Okay? So there are many, we can categorize reinforcement learning in different ways. So here we have a categorization. So reinforcement learning algorithms could be divided into Markov decision process or bandits. That would be when we don't have states. Inside Markov decision processes, we can divide reinforcement learning algorithms between model-based and model-free. In model-based, what we do is that what we learn is the model of the environment. In model-free, we don't have to do that. We just have an agent that interacts with an environment that is not model. Then in model-free algorithms, we could have value-based, that what we have is that we estimate what is the optimal value function, or policy-based algorithms that directly select the optimal policy instead of estimating this value function. And then here in the right side, you can see the different examples of value-based algorithms, such as Q-learning, that it's really it has been widely used, or policy-based, that we could have policy gradient or TRPO, etc. So traditional reinforcement learning had a small problem, let's say. So taking as an example Q-learning, usually what we would do is that for each pair of state of an action, we would store in a lookup table what is the estimated value that we would have if we are in a state and we take that action. So, and this would be stored for all the pairs of stated actions that the agent is exploring. So, and if we have large state and action spaces, using these lookup tables can be really unpractical and unfeasible. So deep learning has given solution to this scalability problem of traditional reinforcement learning algorithms, to the combination of neural networks with reinforcement learning, which is called deep reinforcement learning. So in here, what we have is that the neural network, or the neural network, approximates what would be the Q value for each, when we give a given action. So for here, you can see in the graph that for a given state, the neural network would give us as an output the estimated Q value for each of the actions. So from here, we would select the action that maximizes, that has the highest Q value. With this, we will be able to deal with high dimension of state and actions spaces. And in fact, this has been a key solution and has given the more potential to use deep reinforcement learning in several problems. Again, we may have a lot of different types of deep reinforcement learning that mainly is the application of deep networks to the different traditional reinforcement learning types. So we could have model-based deep reinforcement learning, we have different types, and also model-free deep reinforcement learning algorithms that could be value-based and also policy-based. So from here, let me highlight DeepQ network. That is what's one of the first algorithms that integrated neural networks. And this, based on this, several new deep learning algorithms, deep reinforcement learning algorithms have been created, such as double DQN, DDPG, or action critical based on deep learning, etc. Well, this is a photo of the current deep reinforcement learning algorithms. I have to say that deep reinforcement learning is a current active, it's currently under research. So new algorithms are appearing and are being developed. And there are different research lines that we can devise, that are currently being developed in deep reinforcement learning. One is what is the balance that we have to do between exploitation and exploration phases during the training of deep reinforcement learning algorithms. So how much exploration should I do against the exploitation? Also the generalization problem. So here in this area of research in deep reinforcement learning wants to deal with how to obtain a general policy that is adequate for my scenario. So how do I have to train this model in order to achieve generalization in my deep reinforcement learning policies? Also, we have multi-agent reinforcement learning, where instead of having just one agent, we have multiple agents that in order to learn their policies, they can collaborate between them or also compete between them. There are different approaches. We also have federated learning, where we have multiple actors that learn a common policy. And transfer learning, where in transfer learning, what we have is that we leverage previous knowledge learned from a given policy to accelerate all the training process to learn a new policy that might be for a similar task, but not exactly the same task. And also there is this inverse reinforcement learning that here, instead of learning this policy, what we focus is that we have an expert learner, and we derive from this expert learner what is the reward, what would be the reward functions from that. And we could add more points here. So with this, I wanted to show that although this graph will show the main stable deep reinforcement learning algorithm, this may evolve, and we could add more algorithms there. So, having done this overview of machine learning and reinforcement learning more in a general view, let's move to explain what is the applicability of reinforcement learning in the different domains of the radio access network. So, the radio access network has some interesting features. First, it has variable radio propagation effects, such as path loss, shadowing, and interferences. Also, we could have fluctuation traffic demands from the different services. So during the day, we won't have the same traffic demands in one cell, or even in two cells, we could have completely different traffic demands. Also, we can have multiple traffic types, more in 5G, for instance, where we can have services that have quality of service requirements with really low latency, high data rates, and maybe we would need high reliability, etc. And also, we have really huge neural networks that have heterogeneous nodes. We could have macro cells, we can have small cells, picocells, etc. So this makes the radio access network a highly complex environment. So reinforcement learning techniques offer a solution for radio access network problems that have some sort of decision making, as I advanced before. So this specifically could be especially interesting for radio resource management algorithms and also for self-organizing network functions. So to deal with this, we could learn solutions for this kind of algorithms through the interaction of an agent with the radio access network environment, and if we are using model-free reinforcement learning algorithm, we shouldn't have to model the radio access network environment, which is a really complex task. So using reinforcement learning here avoids us to be able to have to model the radio access network environment. Also, as giving all this highly complex environment, we could have really high state and action spaces, which can be addressed by using deep reinforcement learning. Reinforcement learning could be accommodated in different control loops devised for Open RAN, so for RAN management solutions. So in Open RAN, there are three kind of loops that are identified. The one would be real-time control loops that would be around 10 milliseconds. That would be more associated to lower layers like the distributed unit or the distributed unit mainly. Then we would have control loops and solutions that work in near real-time duration, such as from 10 milliseconds till 1 second, and then control loops that are larger, around 1 second, that are called non-real-time loops. So reinforcement learning can be addressing the solutions associated to this kind of control loops. So here I listed what are the main algorithms that would be associated to each of the control loops. So for real-time control loops, smaller than 10 milliseconds, would be associated to the MAC and physical layers. So with this, in this reinforcement learning would be addressing the MAC scheduling, also at physical layer channel coding, dynamic spectrum access. Well, you have here the different problems. In near real-time loops, here we would be addressing problems related to radio resource management. So, for instance, admission control, power control, interference management, also handover decisions, etc. And for loops larger than 1 second, this would be associated to functionalities of the operation support system or self-organizing networks, such as here I listed different like capacity and coverage optimization, mobility robustness, mobility load balancing, etc. So, depending on the way to apply reinforcement learning has some trade-offs depending on these loops. So, for instance, if we look at the number of impacted users by the reinforcement learning actions, if we are applying reinforcement learning in loops, in really small loops of 10 milliseconds, here the users that will be impacted by reinforcement learning actions will be small. So if our reinforcement learning agent takes an erroneous action that this may have, then the impact in degradation will just impact the users that are connected to a given cell. Instead, if we are applying reinforcement learning to solutions such as capacity and coverage optimization of control loops larger than 1 second, they usually impact a lot of users. So then, if we have a reinforcement learning agent that is not behaving well there, this would be impacting on the degradation at network level and impacting a lot of users there. So this has to be taken into account in the way that we train and we apply these reinforcement learning actions. Of course, we always want that our reinforcement learning algorithm works perfectly and doesn't select erroneous actions, but we need to have this into account. So for those solutions that are being applied in control loops, in smaller control loops, this maybe training directly in the network would be a possibility. Let's see. But also, when we are impacting a lot of users, the training of reinforcement learning directly on the network would be quite dangerous because we could have high degradations there. So this training should be performed offline using simulators or even network digital twins, as I will be explaining later. Another requirement here is the lightweight of the reinforcement learning models. If we need that our reinforcement learning model is behaving in control loops smaller than 10 milliseconds, we need that the algorithm that we select, the reinforcement learning algorithm that we select to address physical and MAC layers problems, we need that this is very lightweight, so we need to optimize the size of the neural networks, the Q tables, etc., in order to meet this real-time behavior. But when we are dealing with problems that are in control loops larger than 1 second, as we don't have this real-time constraint, maybe the size of the model, for instance, the number of hidden layers and neurons, maybe it's not that critical. So although we always aim at having lightweight solutions, this is not something that is that critical in that sense. Okay. So now for each of these control loops, I will show you one example for each of the control loops for you to have a more an idea of how we could use reinforcement learning for each of them. So for control loops smaller than 10 milliseconds, the example that we have here is for MAC scheduling. So a MAC scheduler, what it needs to do is to do the dynamic resource allocation of the available resources to the different users that we have connected to the cell. Also, it needs to take into account link adaptation, where we need to decide what is the modulation and the coding scheme for each of the transmissions. And also, it could also need to deal with the beam management, so that we need to acquire and select the appropriate beam for each for the mobile terminal, also tracking the beam, etc. So here, reinforcement learning could be used to be the algorithm that decides on the different actions on dynamic resource allocation, link adaptation, or beam management. And here in the right side, you have an example for dynamic resource allocation. So imagine that at first we have a certain amount of resources divided in frequency and time. So, and we have 4 users. Each user is assigned with a number of radio resources there. So the reinforcement learning agent here could obtain the state, saying what are the resources that are assigned to each of the users. And then it could decide, according to the requirements or the conditions that have the different users, what would be the action that is made, that would be what are the new allocation of the resources to the different users. The second example that is for the near real-time loops. This would be admission control. So admission control determines whether to accept or reject the establishment of a new session, request at cell level. And in this, needs to take into account that we want to ensure the quality of service of that connection, also maximize the number of connections that we might have in that cell, and also maximize the revenue that the operator have there. So this could have a really large number of states because we can have different services with different quality of service requirements, and this makes this admission control task quite complex. So we could use a reinforcement learning algorithm to learn what is the policy that accepts or declines a new session request. So for instance, here in this graph that we have here in the bottom, we would have a user that sends a new session request to the base station. This base station would obtain the quality of service requirements of this new request, and also the state, what is the occupation that we have in our base station. And then by learning this policy would send an action that says whether to accept or reject this new session request. Okay, and then this. So we could learn a policy that optimizes this acceptance or declination of a session request. And an example for control loops larger than 1 second would be the self-organizing network function for capacity and coverage optimization. Here in coverage and capacity and coverage optimization, what we want is to determine what are the network capabilities in order to guarantee the quality of service of a certain number of customers in a given geographical area. So here we are focusing on multi-cell capacity and capacity. So here what we need is to automatize the configuration of the different cells so that we can optimize what is the number of users and the capacity that we are providing to them. So here we could deal with problems like just the minimization of coverage holes, the reduction of the interferences between the different cells or base stations, and also increase the capacity of the system. For instance, reinforcement learning here could be used to set the transmission power of the different base stations or the antenna tilt. So as an example here, we would have the minimization of coverage holes. So in a given moment, we could have a situation where we have different coverage, when we have holes in a given geographical area. So this reinforcement learning algorithm for capacity and coverage optimization could obtain the coverage that we have in this geographical area, and based on this, configure the different base stations so that we minimize the coverage goals, such as, for instance, setting what is the power of the different base stations or antenna T, etc. Well, with this, I hope that you have more or less an idea of how we can apply reinforcement learning to the radio access network problems. So imagine that you have one problem in your mind that you want to deal with and you want to approach by using reinforcement learning. So in this workflow, you have the different stages that we will need to go through if we want to deploy this reinforcement learning algorithm solution. So we would have a first stage, that is the modeling stage. Then we will have to develop this solution. And then if this solution is good enough, we would be able to deploy this in a production environment. So these are the different stages that we need to go through. So let's start with the modeling stage. So here we would need to first define what is our problem, which are our requirements, our goals, and the metrics that we're going to use to define this problem. Imagine that we want the admission control, it would be our problem, and then with that we would have to select which are the different quality of service requirements, what would be the selected actions that we would do, etc. So after this problem definition, we would move to select which is the most appropriate reinforcement learning algorithm to deal with our problem, and also considering the trade-offs that we would have in for instance, the control loop. If our problem needs to be really lightweight, where we are going to deploy this solution, etc. So this would be something relevant for the selection of the reinforcement learning algorithm. And then we would do the model formulation. Here we would particularize the selected reinforcement learning algorithm for our problem. So for instance, we would define how we define the state. For instance, if we consider the utilization of the resources, or etc. Also, what will be the actions that will be triggered by our agent, and then how we assess that an action is good. So we will have to send the rewards. And also, of course, we will need to make sure that our state, action, and rewards are compatible with the parameters and architectures that we have in the standards. Okay? So, for instance, if we want that our solution is deployed according and it's compatible with the Open RAN architecture, we would need to decide where we are going to apply that reinforcement learning algorithm. So in the Open RAN, as I more or less introduced before, there are different functionalities that allow to deploy artificial intelligence algorithms. In these AI algorithms in Open RAN are called RApps and XApps. So those applications, the AI models that are being deployed in the non-real-time rig, in the service management and orchestration function, these are called RApps. These would be executed, as I said before, in control loops of 1 second or larger. And also, here in the non-real-time rig, we would have also functionalities for the AI and machine learning workflow, including the training and the evaluation of the model. Also, if we are dealing with a reinforcement learning algorithm that it's executed in timescales smaller than 1 second, this would be deployed as XApps in the near real-time rig. So the training of these XApps would be performed in the non-real-time rig, because there we have all the machine learning training structure. And then after this would be the XApp would be deployed in the non-real-time rig, operating in time scales smaller than 1 second. Here, I wanted to mention that recently there is a standardization work in Open RAN to deploy AI solutions that are really lightweight in lower layers These are called the apps, but they are currently under development, and it's not completely official, but there is work there to be able to accommodate AI solutions that are working in smaller smaller loops. This would be deployed in the ODU, for instance. About this compatibility of reinforcement learning solutions with the standards, one thing was that the reinforcement learning algorithm is compatible with the with the architectures that we have, but also it is important that when we define the stakes, the actions, and the rewards, that the different specifications is compatible with the available parameters and performance measurements that we can take from the standards. So regarding the parameters that we can configure in the network, in 3GPP they have these network resource models that, well, here you have the document number where you can find these network resource models for 5G, for the case of 5G. So here we have these information objects classes that define all the information that is relevant to configure certain parameters of our network nodes. For instance, here I included a snapshot of what it would be the bandwidth part IOC, and we have that for this object we have different attributes. For instance, the bandwidth part context, the cyclic prefix, the starting radio blocks that are assigned to this, etc. So for each of these IOCs, we would be obtaining the attributes, and also what are the constraints for the different attributes. To be able to configure this in the base station and the network nodes, these IOCs are defined in what is called Young models, okay? That I will show later. So this would be, by using the network resource models, we could find what are the parameters that can be configured in the network. So this would give us what, for instance, this would be important to be able to define the actions that our reinforcement learning would do, because these actions would be inferring the parameters in the network resource models. But also, if we want to obtain the state from the radius access network environment, we also need to be able to obtain data from the environment. So this is defined in the performance measurements documents in 3GPP. So there are different, in the documents of performance measurements in 3GPP, they define different types of families, such as data radio beater, radio resource control, quality of service flow. So there are different kinds of performance measurements that can be defined. And then for each of them, it's quite well defined in terms of what is the description of each performance measurement, the name, how to collect it, the conditions, the units, also the maximum and the minimum values that it could have, etc. And apart from this, we would also have in 3GPP what is called key performance indicators, that are metrics that are based on performance measurements, are also categorized in different families, such as, for instance, for mobility or energy efficiency, etc., and are all well defined as performance measurements. So with this, when we define the states, the actions, and the rewards of our solution based on the parameters that are specified in 3GPP, at least we would ensure that our solution can be applied to all the devices and networks that are compliant with this standard. Okay, so this is quite relevant. Okay, so with this, we would have our model well-defined and specified to be able to start coding, to start developing it. So during the second stage of this workflow is the development stage. Here, first, we would need to code. So after defining our algorithm, we will need to code it. So this can be performed, we can program the reinforcement learning from scratch, but also we can leverage the work done by others by using different libraries. And also, in this selection of what library to be used, it's relevant to consider what is the reinforcement learning algorithm that we have selected. So, to make sure that that algorithm is available in the library that we select. And also the type of programming language, how customizable is the library that we select, etc. I will give you more examples on this. Also, apart from coding the algorithm itself, we also need to consider that usually during this development phase, this reinforcement learning algorithm will be trained in a simulator environment or in a testbed. So we won't be, during this development stage, training this algorithm directly in a real network, which is something that we could even not do in the production stage. So we will need to code this network, the network simulator, or that, as I will explain, it can also be done by a network digital twin. Also, so first we will need to code the reinforcement learning algorithm and and select the simulator environment, and if we need to code it. Then, based on this, we would be performing the training of the reinforcement learning algorithm so that the agent or agents that we have in our solution would be interacting with the network environment. And also, during this stage, we would do also the tuning of the hyperparameters that we have in the reinforcement learning algorithm. So usually reinforcement learning algorithm, apart from the definitions that we have of the state, the action, the reward, it has also other hyperparameters, such as, for instance, the learning rate. So in this stage, we will be also tuning these parameters. So let me go a bit deeper into the coding of this kind of algorithms for those that are interested in developing a reinforcement learning solution. So usually here we kind of capture what is the general elements that we have in the libraries and in reinforcement learning libraries. So we usually will have an agent, an object that is called agent, that is a representation of the reinforcement learning algorithm. And also it incorporates the reinforcement learning, the dynamic and the code of the reinforcement learning algorithm, and it includes also the policy. That, as I said, it would define, given when this agent obtains an action, obtains an state, this would be outputting the action. Also, these libraries will have some object called environment, that this would represent what is the task that needs to be solved. This environment could be based on an already developed framework that we could have, or also can be, we could develop it ourselves. So at least this environment will need to provide states to define what is the situation that we have in the environment. We'll be able to receive actions and configure the nodes or the elements that need to be impacted by the actions of the reinforcement learning agent, and it also would need to provide the rewards from this environment, assessing how good or bad were these actions. Also, usually the reinforcement learning libraries have this element here in the middle that is called driver, that it manages the interaction between the environment and the agent so that the formats of the different elements are compatible. And also, as an output of this, we would have the agent would provide training KPIs to be able to assess the training evolution, and also we will always have some kind of data processing and analysis of the training of this agent, and also to be able to evaluate the policies of our agents. Usually these algorithms, these libraries have two ways of using them, one for the training itself and also another for evaluating the trained algorithms. So during training phase, we would have that in the agent, the policy that we will have them, we would be an exploration and exploitation policy. So this would be an epsilon greedy policy, as I said before, that with certain probability takes random actions, and if not, it exploits the current model of the agent. And then in this training mode, we would be storing all the rewards, the actions, and the rewards to update these reinforcement learning models, and we will be obtaining training KPIs to see if our policies are converged or they are behaving as expected. Then during evaluation, instead of having this exploration and exploitation policy, we would also only have in the agent the exploitation, the policy that we had previously trained. So we would be not selecting this random action. So this is why it's just an exploration policy, and the reinforcement learning algorithm would not be activated, so that we would be just applying the policy that has been trained before, and then we would be able to, for a given situation that we want to assess our policy, and then we will be able to see what is the behavior of the policy that has been trained in that situation. So here in this table, you have different libraries, Python libraries, that can be used and that incorporate a reinforcement learning algorithm. And for each of them, I included each of them will have a number of reinforcement algorithms that are supported. Also, as you can see, the different reinforcement learning algorithms may support different number of reinforcement learning algorithms. For instance, stable baselines is a really complete library in terms of the number of reinforcement learning algorithms that are included. But when selecting this reinforcement learning library that we use to develop our solution, we might have into account the other criteria. For instance, the documentation that we have of this reinforcement learning library. So as this is usually open source, it's good to have good documentation. So for instance, TensorFlow agents, the quality of the code is very good, but the documentation is not quite complete. So this would be something to have into account when selecting a reinforcement learning library. But for instance, TensorFlow, the quality of the documentation is quite good. Also, the code, as we will be usually will be able to access the code, we can see how good it is coded, and if it's easy to follow the code, this would also ease the task to code the reinforcement learning solution. So in this case, for instance, in the case of TensorFlow agents, the documentation is not very complete, but instead the code is very well commented. So if you need to make some changes and to particularize some functions, it is easy to do it. Another criteria when selecting this Python library would be if it's the environment that it supports. So there are reinforcement learning libraries that allow to have an environment that is so they fix what kind of environment you can use, or they just leave it open. For instance, for the case of TensorFlow agent, the environment is agnostic, so you can plug any environment that you want to perform the training. For others, for instance, in the case of TensorFlow or reinforcement learning coach, they give you links to be able to deploy your environment in OpenAI Gym, that is a platform that gives you environments to train reinforcement learning agents. Okay, so depending on which kind of environment you will use to train your agent, then you would select one library or the other. And also, maybe if you can just select your reinforcement learning agent as it is, maybe you don't need to customize the code, but it is something that you could also consider. If you need to make some changes in the code, you need to consider a library that supports it and that makes it easy. So here I included this screenshot of one of these libraries for you to see how it looks like. So this would be for the example of the TensorFlow agents. That is an open source implementation of current state-of-the-art deep reinforcement learning solutions, and this is coded in Python. So this would have the different elements that I previously told you. So we would have the agent, we would have the driver, also we have the Python environment. So this would be the TensorFlow agent system. And the main benefits of this library would be that it can be easily customized, it has a lot of tutorials, the code is quite clear, and it has a large community. So, for instance, in the example that I will show you later, I will be using this TensorFlow agents library because it had the reinforcement learning algorithm that I had selected for my problem, so I decided to use this. So during this training of the reinforcement, during this development phase, as I said, there is one thing is coding the reinforcement learning agent, but also we need to consider the environment. So the training of the, as more or less I advanced it, but the training of this model during both, at the end, during this training phase, it needs to be performed in a simulated environment, usually. This is because the reinforcement learning needs to, during the training, needs to do this exploration through not greedy actions, so to random actions. Also, if we do this directly on the real run, this would lead to unacceptable degradations in the network performance. So imagine that we want to train this reinforcement learning algorithm that we have developed and is not tested in a real environment. This could affect a lot of users, leading to unacceptable degradations, etc. So for this, we would need to do this training on an offline simulated environment. And usually, when training these reinforcement learning agents, we want that the training includes the situations that will be seen in the real network, in order to ensure that the agent is able to behave correctly when we deploy it in the real environment. So for this, usually, to perform the training, this would be capturing and using offline historical data gathered from the real environment. So in order to address this offline training of the reinforcement learning algorithm, the network digital twin has been identified as a potential solution. So what is a network digital twin? So it is a virtual and updated representation of the network that brings the possibility to analyze, diagnose, and emulate different physical network in a zero-risk environment. So at the end, it's a simulated environment, but it's updated using real data from the real network. So here we would have that from the real radio access network, we would obtain, and we will collect data, and we would build, based on this data, a radio access network digital twin, and then this could be exploited for different uses. One use would be, for instance, for planning and dimensioning. So imagine that we want to deploy new base stations or new cells or new configurations of the network. So we could assess where to place these base stations in a network digital twin to see what would be the resulting coverage or capacity in the system. So this would be the application of network digital twin for planning and dimensioning. Also, this could be used for network operation. So if we are updating this network digital twin, we would monitor in real time and the network, and also detect anomalies by using prediction functions in the network digital twin. So we could also use this network digital twin for network operation. And also, if we want to tune different parameters of the network to see what is the impact, this could be used for network optimization. And finally, for the use case that is relevant for this presentation would be the use of the network digital twin to support the training and evaluation of the reinforcement learning solution. So we could use the network digital twin to capture what are the situations that it will have in the real environment, and then to perform the training of the reinforcement learning algorithm in a zero-risk environment, that is the network digital twin, without affecting the real network. And in this case, we would have the policy that we will be learning is a policy that knows how to behave well in the same conditions that we have in the real network. So here you have an example of how could be a network digital twin interrun that is in a previous publication of our group. Of course, this network digital twin could take different forms, so this is just one proposal of how could this be. That is so it includes, this has different blocks, as you can see. First, we would have a data repository. That this data repository, what it would do is to obtain data from the real environment and would store it, then to be used for the rest of the models that we would have in the network digital twin of the RAN. Then we would have serving mappings models that what they do is that they represent the different elements and functionalities of our network. So these are split in two main types. We would have the basic models that represent the radio access network entities themselves by capturing their configuration and in the real network. So for instance, we could have in these basic models, we could have the scenario topology, the G-node piece and their configuration, the users, and the type of users that we have, and other aspects such as the channel, the type of characterization, or if we are using network slices, so the specification of the network slices. Also, we could have, apart from these basic models, the functional models that include different, from one side, different run management and optimization that we could have in the real network. For instance, some functions, radio resource management policies for that mission control or resource allocation, and also for handover, etc. So these would be captured here in the functional model. Also, these functional models will include some functionalities for emulating different situations in the network digital twin, for instance, generating traffic and different traffic generations. And all these, and finally also exploitation models, so is to monitor and to export the different metrics that we have here of the rest of functional and basic models. So in general, all the data and all these models would be based on the data from the data repository. So for instance, imagine that we want that in our digital twin to generate a realistic traffic. So this would be the data regarding the traffic volume could be stored in the data repository and then fed to the traffic generation, that model that we would have in the network digital twin. And then we would have finally the digital twin management block that we would have different functionalities for managing the life cycle of the network digital twin. For instance, if we want to activate certain modules or we want to deactivate different modules, also how to control the emulation dynamics, and also to be able to gather all the errors, and etc. So for a given reinforcement learning agent, if we want to use the network digital twin like this to perform the training of a reinforcement learning model, what we would do here would be to specify what are the modules that we need for our network digital twin. For instance, imagine that we need network slices, so we would need to activate this module, and then we will configure the network digital twin to do our training, and also we should have to specify how we use the data from the real network in this network digital twin. So with this, we would have our model defined and also developed and trained. So now let's see that we see that our model is really good, and then we want to deploy it in a real network. So then we will be at the third stage, that is the production stage. Okay, so with this we will do the model deployment and the model monitoring. So the model deployment, we will need to, it covers all the tasks that we need to do to prepare the model to be deployed in the real network environment. And then also we will need to have some kind of model monitoring in order to assess if our model is behaving well, if it has some problem and it's leading to some degradations there. So if we detect this, then maybe the model needs to be retrained. So we will be going back to the model training, where, for instance, we could be updating the network digital twin that we are using to train our model and then deploy it again. Okay? So in the production stage, we will need to do this. So first, I wanted to clarify that when we are in the production stage, usually in order to deploy our reinforcement learning solution safely, what we would do is that we will perform the reinforcement learning model inference. So this is when we apply the train policies in the run environment, but usually without exploration. So we will not be doing this selection of random actions to explore. So first we train the model, and then we do the inference in the real environment. So in this case, the reinforcement learning agent, the model will be frozen, and we will be just sending the actions. So in terms of software, we will need to take two actions there. And the first one would be to be able that our reinforcement learning agent is able to interact with the network. So we need to implement the interfaces to obtain the states and send the actions. And also, we will need to prepare and package our solution to be deployed in the production platform. And also we need to include some management of the different policies, etc. Okay, so maybe we can kind of, well, I will continue just two slides, and then we stop for lunch. So here we would have what is we will need to manage the reinforcement learning solution for during this production. So this is the ORAN framework that we have for the deployment of machine learning solutions, where we would have that the training is performed in the machine learning training host that would select what is the environment specification. For instance, selecting the network digital twin. It also includes functionalities for the model optimization, okay, so for tuning the hyperparameters, and also for refining the model if we need a retraining. Also, after training this policy in the machine learning training host, they will have the model management. So it would obtain all these models, and then decide which of the models that have been trained is performed for the inference. Then this would be inferred in what is called the machine learning inference host and actor. So here, the model deployment is performed in the model inference engine, and it also includes a functionality for the online training if it is supported by the solution. in order to support this monitoring that I was telling you about during the inference, we have this continuous operation that it obtains different functionality, different data from the network, and then makes some verification, an analysis of this, and if it's detected that the scenario changes or that the reinforcement learning agent is not behaving properly, then this would be notified again to the model management, and then maybe a retraining of the model could be selected. This retraining would be triggered by the model management. It would select that new data is obtained from the environment, and then that a retraining is performed. Okay, so if we want, we stop here, and then in the second part, I will continue.
Thank you. Any questions, anyone?
So, very good afternoon to Dr. Iron Vola. So, I am Dr. Shiv from Computer Science and Application Department. So, first of all, thank you very much for the insightful presentation on reinforcement learning on 5G. So, I have two questions. One is related to what are the bases to implement reinforcement learning in 5G. This is one. Another is the how do you see the reinforcement learning to enhance the network optimization, especially using the reinforcement learning in the 5G, and how to handle this because the 5G is very fast network, and particularly in the real-time scenario, the demand of the network.
Okay. In the second question, could you repeat it?
So first question is, what are the bases to implement 5G, to implement reinforcement learning in the 5G?
Okay, so as I was telling at the beginning, reinforcement learning allows us and gives us the way to learn policies to address decision-making problems in 5G. So if we need to configure certain parameters that are really complex, we could use these reinforcement learning algorithms to select which is the best control decision, and each time depending on the situations that we have in the network environment in general. So based on this, we could, this is the interest of using these reinforcement learning algorithms, because they allow to derive decision-making policies.
So had your team implemented or deployed this model, hardware as well as
yes,
software?
in the second part of the presentation, I will show you one example in detail, so maybe you will have a more illustrative example for this. In this case, the algorithm that I will be showing is an algorithm for capacity sharing in a scenario with network slicing.
Okay, so I think you also got some result like how this reinforcement learning in the 5G will handle the lot of data, particularly the demand of the network. That was my second question.
Yeah.
Thank you.
Any other question, anyone?
Hello, ma'am. Thank you. Very nice talks, ma'am. I have just some basic query regarding the AI and ML and deep learning. How can apply the AI in the biomolecules like that brain mapping activities? If it is possible, so what is the basic parameters of the AI?
Hey, could you please, could you? Oh, okay, so you mean if this is applicable in the network?
Yes.
Yes, all these 3GPP and ORAN, etc., they are working to see how can we apply all these kind of models in the network. But of course, there are a lot of challenges there. Because if we want to deploy these AI models in the real network, we need to make sure that they are safe and that we can trust them. So apart from just the development of these AI models and reinforcement learning solutions, we need to incorporate in this network functions and elements that allow to control them, and that they are, for instance, that the training is well performed, that the data that we are using is safe, that there are not privacy concerns there. So regarding your question, I think that technically we could achieve really good algorithms, etc. But the key to apply this in the network at the end would be that we can trust these algorithms and that they are not that much complex than an heuristic algorithm, of course. I mean, this technology is very, very nice, but we also need to be critical and to see if it has sense to develop certain solutions. Of maybe what we have is already good, and also having all these functionalities for trusting these algorithms.
Thank you.
Hi, Irina.
Hi.
Yeah, I think I am not a man of, you can say, machine learning or maybe these deep kinds of models. I am heading here physics department and environmental science department. My question is that as a layman, what are the parameters to define this 4G, 5G? What are the parameters on basis of that we can define that this one is 4G or 5G? Second question is that in coming 2025, could we expect 6G, 7G, 8G? Where is the limit?
Oh, okay. So, if I understand well your question, you are thinking of if what we design now for AI with the current parameters in 4G or 5G, this will hold for future networks, right? Yeah, I mean, I think that this will be even more supported, because in 4G and maybe in the initial stage of the definition of 5G, maybe the use of AI, maybe someone was thinking about it, but it wasn't that much extended there. So at least with 6G, the current work on the standardization and the projects that are defined in this 6G, they are already covering and having into consideration this AI, and in fact is one of the main elements there. So I suppose that with the definition of 6G that it would be AI native, we will learn a lot to see what are the functionalities and that need to be implemented there. And I suppose that, of course, I cannot see the future, but I could imagine that in future networks it will be much more developed.
Since you are expert in this area, so could we expect in coming 2025 with 6G or 7G? What is it?
This is a very difficult question. I would really like to know what will happen for 7G.
Okay, thank you.
Anyone else? So one last question from my side. See, 5G particularly, we know that ORAN is one very important part of 5G. And if we look at the Indian scenario, so though we have already tried and tested 5G in some aspects, but then what do you think would be the major feature where AI is going to be the more impactful while implementing the 5G and maybe the 6G systems? What could be the major challenges which we feel that, yes, through reinforcement learning only, these challenges of 5G and 6G, the kind of network which we are going to expect, the speed which we are expecting in 6G, and the kind of very heavy user density that we will be able to handle using 5G and 6G networks. So what major challenge which you feel that this is something where reinforcement learning or maybe other forms of machine learning are really going to be helpful in implementing the 6G systems?
Yeah, so I think that in general, machine learning could help in a lot of functionalities of RAN in general. As I said, for reinforcement learning, I think it's quite useful for decision-making problems. But of course, maybe there will be developing new algorithms that are more efficient, that are more trustworthy, and this could be dealing with this. But also for instance, for supervised or unsupervised learning, there are a lot of other applications, like for instance, estimating the mobilities or etc. And of course, what we will see, I think that, for instance, this generative AI will be quite, we will need to see if the generative AI has a place also there to deal with other problems. I think that in general it can be quite useful in a lot of problems.
Thank you very much for this enlightening talk. I think we have got a quite clear understanding that how this reinforcement learning is going to help us in further future designing and implementation of the 5G and 6G based systems and other radio access networks. Thank you very much for handling all the queries. May I request Dean Research, Dr. Bhuvnesh Kumar, to felicitate the speaker. Please. No, just please.
Okay.
Only one. Thank you. We'll take a break for the lunch. All the guests, registered participants having food coupons, please reach first floor of this particular block for the lunch. All the students and faculties, they can go to the 5th floor for refreshment. I repeat, all those, the registered participants who are having food coupons, all the guests, deans and directors, they please go to first floor of this particular building. Students and faculty on 5th floor. Thank you. So we'll join back for the session at 2 p.m. Please change the screen.
Okay, thank you. I hope you have had a good lunch. So let's continue with this tutorial. So before the lunch, I introduced. We were revising what are the different stages from the design till the production of reinforcement learning algorithms. So at the last, what that I was talking is that we need to be able to manage the the reinforcement learning model once it's in production. And another aspect that is relevant is to be able to prepare this reinforcement learning solution to be able to interact with the network elements. So if we focus on the ORAN defines different open interfaces that need to be implemented on our solution in order that the solution can interact, for instance, with the distributed unit or the central unit or the radio unit. Okay, so if we have a solution that is deployed in the non-real-time rig, in the SMO, then we will need to implement the O1 interface. Okay, that is the one that is marked here. This interface is organized in management services, this MNS, and there can be different management services. Here I included three. One is the provisioning management services that it allows to configure attributes through the netconf protocol. Also the fault supervision management service that uses REST HTTPS, and also the performance assurance management service that it allows to obtain performance measurements from the network elements. It can be file-based or streaming-based. Also, another interface that is relevant here is the A1 interface, that on the one side, it allows that when we train a model in the non-real-time rig, that it needs to be deployed in the near real-time rig. This interface supports this, but also it supports the model management in the near real-time rig. And also, if for the training of a solution that is deployed in the near real-time rig needs data, this interface is also the one that needs to be implemented. And this is based on policy statements that are encapsulated in JSON format. And then, if we have a solution deployed in the near real-time rig, it will need to access the underlayer functions like the central unit or the distributed unit. And then this is done through the E2 interface that exposes configuration information of the underlayer functionalities, and also allows to obtain data from these functionalities. It's based on this protocol called E2 application protocol, that it has interfaces for this management, including services such as reporting, insert, control, and policy that can be combined to obtain different service models that are similar to the management services that we had for the A1, like O1 interface. So when implementing these reinforcement learning applications that can be R apps or X apps, depending where we deploy them, then we will need to include in the development the different management services to implement these interfaces. Another aspect that is relevant to prepare the reinforcement learning solution that we develop to be deployed in a production platform is that it needs to be well packaged to be deployed in this platform. So in this, we need to take into consideration the virtualization of the network, that at the end, this virtualization leverages the advances in virtualization technologies in general. So we have that instead of having a device that is just for one case, we can virtualize it using, for instance, network function virtualization. And then these network functions could be deployed in general purpose servers, which is much more flexible. So here I just included an evolution from the traditional deployment from the container deployment. So traditionally we would have a hardware with an open operating system where on top of it we would be deploying different applications. Then we can virtualize it so that we can have on top of this operation system, we need to install an hypervisor. And then on top of this, we can install different virtual machines that have their own operation system, is their operating system. And based on, and on top of this, we could deploy the applications in each of the virtual machines. But the latest approach, and that is the one that is being adopted by several, in general, but also by operators and infrastructure providers, is the container deployment, where instead of having an hypervisor on top of the operation system, we have a container engine that instead of having virtual machines, what we have is what it's called container. This container is a virtualization approach in which applications run in an isolated manner as software units that are called containers at the end. Then all these containers, in comparison to virtual machines, they share the same operating system, and each container has the application software and all the binaries and libraries that are needed to run the application. And this the container engine is used to automatize all the deployment of the different applications. This containerization is the candidate to deploy these X apps and R apps. Another approach that is relevant here to consider when deploying these and preparing these applications is that as in operators, the number of containers that we might have and applications deployed on them can be huge. We need some orchestrator that allows to deploy and to automatize the deployment and management of all these containers. Okay, here I wanted to highlight Kubernetes, because if we have several nodes where we have to deploy different applications in different nodes, that it could be different servers, then Kubernetes can be used to dynamically deploy the different applications in the different nodes. And well, this is an open source platform, and it's widely used. Okay, here just for you to know that the containers can be grouped in pods. That is the smallest element of management in Kubernetes, and then we would have elements for managing them, such as the kubelet or the control plane. Okay, so with all this, I've covered all the stages that we have from the design to the production of reinforcement learning. But now let me give you an example of a solution that is, and we will cover all this, I will explain for each of the stages that I have previously described how we have done it for this particular solution. Okay, so here the problem regarding the modeling stage, in the problem definition, we found that we wanted to have a solution for network slicing. That network slicing, for those that are not familiar, is a key technology in 5G, a key feature in 5G that allows sharing a common mobile network infrastructure among multiple communication providers, tenants, so that we can satisfy the requirements that the different tenants have. So this allows to deploy, in order to deploy these network slices in the radio access network, we need mechanisms that allow to efficiently distribute the resources that we have in the network among the different tenants. Okay, so for instance, in the image, we would have 2 tenants, and then we have to assign the amount of resources that are needed by each of the tenants in the different nodes. But as you know, in the radio access network, we don't have infinite resources, so we need elements and mechanisms to be able to efficiently share this. So we designed a solution when we have that it's called a capacity sharing function, that what it does is that it dynamically adjusts the capacity that we provide to each tenant in time steps of delta t, okay? So for this case, what we had was k tenants, that to each of these tenants, we establish a service level agreement with the infrastructure provider. This service level agreement is defined in terms of the system aggregated guidance bit rate and a maximum cell bit rate that can be provided to this tenant. Okay, so then this capacity sharing function will be assigning the capacity of to each tenant in each of the cells dynamically, and this is done by specifying what we call the capacity share, that is the proportion of the total capacity that is assigned to the tenant. And then we have different constraints so that we don't provide more capacity than the available in the cell, and that the capacity share is not larger than the maximum cell bit rate that we establish for each of the tenants. So in order to, once we had that this was our problem and our scenario that we wanted to address, then we said, okay, which algorithm should I use? There are several. So what we did is that we said, as we have multiple tenants, then we will have a multi-agent reinforcement learning approach, where we have that each tenant is provided with a DeepQ network agent. Then the multiple DQN agents that are associated to the different tenants interact with the network environment, and then we can obtain through 3GPP performance management services the parameters that we need from the network to build the state, and then we will be providing the states of each of the tenants. So after this, we started with the model formulation, where we said exactly how we formulate the state, the actions, and the rewards for this solution. In this case, the state was defined by defining what for each of the tenants and each of the agents was obtaining what is the state of the tenant in each of the cells, including the resource usage, the available resources not used by any of the tenants, and the available capacity share not assigned to any tenant, and also service level agreement parameters of the tenant in the state. Then the actions were defined as a multiple component action, where for each agent, the action includes the particular action of that agent in each of the cells. This is defined as the increment or decrement of the capacity in the share in the cell, which can be increased by delta, maintained, or decreased by delta. So each of these components would be a delta, 0, or a minus delta. And these actions need to ensure the limitations that we have for the capacity share. Then the reward, we specify it as by two factors. The first factor promotes the satisfaction of the service level agreement, and is defined by the formula that we have here, which I won't go into detail. And then we have a second factor that measures the capacity over provisioning, so that as a target, we have that no more capacity than the one needed by the tenant is provided to the tenant. Okay, so with these two factors that have their own weights, we define the reward. So each of the agents in the solution is indeed a DeepQ network agent. Okay, so the agent in the QN agents, what we have is the policy that we tune is defined as the maximum of the Q values, where the Q values are approximated by a deep neural network that has weights. So during the training, what we will do is that we will collect the different agents. We will connect different performance measurements from the network. The agent will be sending actions, and then they will receive the rewards, and all these that are called experiences, they will be stored in an experience replay data set, and then the weights of the neural network that approximates the Q values are the average mean square, are updated according to the average mean square error of the loss of the weights obtained from a mini batch of the experiences obtained from the experience replay. Okay. Then, as we have a multi-agent solution, it has some particularities, so we needed to have a block here to obtain the different actions, and that the actions sent to the environment are feasible. This was to verify that the sum of the capacity shares configured by the different DQN agents do not exceed the cell's capacity, and in case this happens, then how to distribute the requests to satisfy the requests of the different tenants. Okay, so this was at problem formulation level. This is what we did. And also in this modeling stage, we make sure that this solution was compatible with the standards. As I said, this is something really relevant if we want to deploy this solution in a real network. So what we saw is that this problem of capacity sharing maps to a problem identified by 3GPP self-organizing network use case that is called cross-slice network resource utilization. And then also we were able to map our solution with the ORAN architecture, where we can perform the training in the machine learning training host of the ORAN, and then perform the inference in the machine learning inference host and actor. Also, in order to interact with the network elements, it's important as this solution could be deployed in the non-real-time rig, in the SMO, so the interface that is needed to be implemented is the O1. Also, we could map the solution with 3GPP and GSMA parameters. So in GSMA, they have different templates that define different service profiles for tenants. So this, we could map it to the service level agreement parameters in our solution, the SAGBR and MCBR, and also the parameters, the capacity shares, that is what the capacity sharing solution is configuring, could be mapped to network resource management models of 3GPP regarding radio resource management policies. So in these resource models, there is one object that is called RRM policy, and the attributes of this object can be mapped to the capacity shares. These are these radio resource management policy dedicated radio, and also to specify the tenant, the radio resource management policy member list that would be the tenant that is associated to a certain capacity share. Also, we also make sure that the parameters that we need for obtaining the state and the rewards are well mapped to 3GPP performance measurements. So here, as we need the utilization of physical resource blocks, then we could obtain it. Also, the total available physical blocks that we have. So in this case, we could map all the parameters that we have in our solution with standardized parameters. So the solution is compliant with the standards. Also, we have developed this solution. So here you can see that we have this development available online in this GitHub that it's here in this link. So, and I want just to mention that if you are interested in seeing how this is look like, there are different tutorials where you can see how we train the solution, how we make the inference, etc. The development of this solution is in Python, and we used the library TensorFlow agent. So here is a diagram of the different elements that we implemented using the TensorFlow agents library. So we had, for each of the tenants, we created an object of the DQN agent, including also the experience replay that is needed for DQN, and also a TensorFlow environment object that is needed that it worked as a driver. Also, we implemented a Python environment that is self-developed, and then it includes a scenario controller that manages multiple cells, and then we have multiple cells. Then for this development, we have the inputs, including the network agents configuration and the scenario configuration, and then as an output, we can obtain policies and also training evolution results from the agent part, but also from the environment, we can obtain also KPI results. This was the scheme that we have to conduct the training, and then a simpler development is made to be able to evaluate policies that have been previously trained. So in this case, if you see, it's a similar, the Python environment is the same, but in the agents, instead of having the reinforcement learning algorithm and the experiences replay, we just need to upload the policies, and then we just have to apply the action. So it's a simpler development. And from this, we can obtain the performance measurements from the Python environment. So the training of the solution needs to be well specified. This can be performed, this could be performed in the machine learning training host of OpenRun. And then we include here that this would be deployed in the model training and testing, where we would have the agent of the capacity sharing solution with the training environment. This would be the Python environment. But then in order to specify how to do this training, on the one side, it's important to specify the number of tenants that are needed, that will be considered to train the solution. Also, how the specific parameters for the service level agreement, the number of cells that it's going to be configuring the capacity shares by the solution, and also other aspects that are more linked to the environment. For instance, we could have the cell configuration, the cell distributions that we have in the environment, and also, in order to test the solution and to consider a lot of experiences that are relevant, we need to incorporate here different training data. This data includes multiple temporal patterns of the offered loads, of the traffic demand that we have of the different tenants, and also different combinations of the service level agreement. Then the model optimization here optimizes the hyperparameters of the DeepQ network solution and the capacity sharing solution, and this is done through a try and error process. So after developing this solution and also training it as I described using multiple training temporal patterns, then we were able to assess the solution in different relevant situations for evaluation. So here you have an example of how this solution behaves. So initially here in the left, we have the offered loads of 2 tenants in blue and in orange that are requirement, that is the traffic requirement in a certain, during one day in a cell. So, and then also in green, you can see the aggregated offered loads by the 2 tenants. So, the offered loads of the 2 tenants, you can see that are complementary. So during the beginning of the day, tenant 1 requires more offered load, and then it lowers during the midday, and in the afternoon it's high, it increases again, while for tenant 2 it's the complementary behavior. And also the aggregated offered, you have here in gray the total capacity in this cell. So during some moments, the capacity required by the two tenants is more than the one available. So let's see how our solution is able to distribute the capacity to the different tenants. So we train the solution, the capacity sharing solution, and then we obtain these policies and we apply it to this situation. So in the graph in the right, you have the assigned capacity to each of the tenants, where you can see that when there is enough capacity, it assigns the required capacity to each tenant. So you would have it in gray and in yellow. But during the moment that the cell, we are requiring more capacity than the one that is available, the capacity sharing solution allows to at least provide the service level agreement capacity. So it's the minimum that had to be assigned, but it allows to avoid that satisfying the capacity of the both tenants. So with this, we could verify that our solution was behaving well. While initially this was trained and operated with a simpler Python environment, then we also test this in a network digital twin. So here, for this network digital twin, we considered a scenario topology that were different base stations in an area in Barcelona. And then we specified the user equipment model, including the user density, the type of users, also the antennas of the user. Also, we specified different parameters of the G-node B model, including the G-node B position, the operation frequency, the power transmission, power, etc. Then also we characterized there the channel model, that it was based on this signal and inference noise ratio and other factors for making it more realistic. And also here we included a network slice model. Also, we included different functional models for traffic generation, for the mobility, also for RAM management. Here we included the parameters for the capacity sharing solution, and also a resource allocation model to assign the physical resource blocks to users. Also, we included a propagation model and different exploitation models to be able to assess the solution, etc. So with this, we obtained similar results than before, but in a more realistic environment. We have also implemented this solution. This implementation is ORAN compliant. Okay, so for this implementation, we considered we implemented the O1 interface in ORAN. So specifically, as I said before, this O1 interface includes different management services, and here we implemented a provisioning management service to be able to configure the capacity shares that specifically they are configured by tuning the parameter radio resource management policy dedicated ratio that is defined by CGPP. And also we implemented a second management service to be able to gather information from the ODU, since the solution, this radio resource management policy is configured in the ODU. Okay, so for the configuration of the radio resource management policy ratio, this provisioning management services was implemented, and this is based on a protocol called netconf. Okay, this protocol allows to create, delete, modify different management objects instances in a management service provider. So here you can see the main layers of the netconf protocol. So it builds upon SSH, and then it works with RPC, the remote procedure call. Then we can do different operations like get, config, to edit configurations, etc. And then the content would be the configurations that we need. So in this, this would be the flow that we'll be doing to be able to configure these parameters. So first what we need is to establish the netconf session, then the provisioning management consumer, that in this case, this would be the capacity sharing solution. This would say, okay, I want to edit a certain configuration, then the object that we are modifying in the management service provider would be modified, and then this a reply on this would be sent. So in order to perform this, it is important to configure this configuration of the radio resource management policy ratio is defined by using Young models, a Young module, right? Okay, so this Young model is defined by 3GPP and specifies what for each of the parameters different fields that need to be provided. For instance, for the capacity sharing solution, here we can specify in the Young model. It's specified like the type of resources, also what tenant will be provided with this configuration, and then the capacity shares that we are specifying for each of for the tenant. Okay, so while the fields of this radio resource management policy ratio are defined by Young, then the values are provided by XML configurations. So here you have an example of an XML configuration that configures the radio resource management policy ratio of 2 tenants. So here in the ID, what we would have is that we are configuring the parameters for tenant 1. We would be specifying that we work with physical resource blocks, and then we would specify in the field of radio resource management policy dedicated ratio that in this case that 60% of the physical resource blocks are provided to this tenant. Here we would have the configuration for the second tenant. Okay, so with this, let me show you how a test that we did for this configuration. Well, here is the deployment that we have with a netconf server. So here we implemented this configuration of the radio resource management policy. This is the code that we considered. We established the IP to configure this parameter. So first, what we did is that we ask what was the current configuration in the base station, and with this, it was said that tenant 1 was provided with 80% of the capacity, and tenant 2 the 20% of the capacity. So based on this, we said, okay, we want to make another configuration. So we built this code that it implements the netconf protocol, and here instead we said that tenant 1 would be provided with 60% and the tenant 2 with 40% of the capacity. So we tested this, and then we could obtain again what was the new configuration that was sent to the ODO. So with this, now I was obtaining the new configuration. I suppose I run this. So with this, we could see the result. We retrieved the new configuration, and as you can see, we could satisfactorily obtain that it was 60% for tenant 2 and 40% for tenant 2. Okay, so this was what we did for the management, for the configuration of the radio resource management policy ratio. And the other service that we implemented on the O1 interface was the Performance Assurance Management Service. In this case, there are two types of files that can be obtained. One is the performance, the performance data obtained in a file-based manner that then it's not in real time. And then it could also be implemented by data streaming. In our case, we selected the data file base because our solution will be running in the order of 3 minutes, so we can rely on files. So here, what is important for this implementation to obtain the performance measurements is to understand what are the formats that will be obtained from the network elements, from the base station. So this is specified by 3GPP, which specifies how to the scheme that we will have for the performance measurements. So for instance here, it was specified the information regarding the different parameters in the state. Specifically, here we were using the physical resource block used by the two tenants, that this would be this parameter there. It's not working, okay. So, and also the physical resource block available. So with this, when it says MEAS type, this specifies the parameter, and then when we have below we have the values for these different parameters. So we also implemented, and also we could also obtain values for the throughput. So this is how the performance measurement data is provided. Okay, this is the format, but it's important that we are able to trigger, to obtain this data, from the base station. Okay, so we also implemented this, and this is performed by implementing this scheme here. So once we obtain, once we are notified that we have a new file available, we can download it through SFTP, as it is specified in ORAN and also in 3GPP. So let me show you how we did it. So we had this SFTP client that was simulating in the base station. So in there we obtained that we have a new performance measurement file. So we implemented the Python code to be integrated with the DeepQ network's capacity sharing solution to download a new file from the SFTP server that is in the base station. So here we were provided with information of the name of the file, also the name for where to download this new performance measurement file. So, and also to be able to read the data from the performance measurement file. And that is the format that I was showing you before. So here we could download this, and I suppose that this will be run now. I run this script. And from this, we could obtain from the SFTP server the performance measurement configuration that included the physical resource blocks used, the physical resource blocks available, and also the throughput that we had for each of the tenants. So after this, for the solution that we built is that for the different tenants, we built a capacity sharing container that it included all the libraries required to run the different reinforcement learning agents. This included Python, the Python version, and also the TensorFlow agents library. And then the application would be the capacity sharing code, including also the netconf clients and to make configurations, and the SFTP client to be able to perform to obtain performance measurements. So at the beginning of each session, what this code does is that it establishes the netconf session and the HTTP TLS session for obtaining performance measurements. Then this application, what it does is that it loads a previously trained policy from a policy database, and then we would be receiving this at each time step. When a performance measurement file is available, it would notify it. And then we would obtain the performance measurement file, we will process it, we would generate the state based on these performance measurements, and then we would apply to this state the policies, and then we would configure the radio resource management policy dedicated ratio based on the result of the policies. And then finally, this, the value of the radio resource management policy ratio would be configured through netconf to modify an attribute in each of the cells. So this is the scheme of the production solution that we had. So as I described, in this container, we had the code of the capacity sharing inference, of the inference of the policies of the capacity sharing container, and then for each of the cells that were managed by the solution, we had a netconf client and a performance measurements client that at the end it would be at HTTP, TLS, and SFTP connection. The operation of these two boxes would be the one that I showed in the videos before. Then in order to test this, what we did is that we implemented a simulator of the distributed unique network function through having, for each of the cells that we wanted to test, a netconf server that it was loaded with the young models to be able to understand the capacity sharing, the radio resource management dedicated ratio for each of the tenants, and also a performance measurement server that it generated the performance measurement files. This was just to test this O1 interface, that the result was the one that I showed you for each of the services. So this is what I was explaining to you, that here you can find where we obtained the servers for the distributed unique network function simulator. We didn't develop it, we downloaded it. So now let me leave the floor to the Professor Uriol Sallent, that he will give you what is the context of all this work that I have been presenting.
So good afternoon, everyone. First of all, I also would like to thank the organization of the conference for including this tutorial, and I hope this is going to be interesting to you. So after all what Irene has explained, I would like to give you some hints on the research context where we apply this work. So we have in our research group at Universitat Politècnica Catalunya, we've been working in, let's say, different aspects of artificial intelligence applied to radio access networks in context of 4G, now 5G, and now starting to think also on 6G. And then I will, as I said, I want to just describe briefly, let's say, in which type of projects and what are the elements that we are, let's say, exploiting these concepts. So maybe some of you are aware, some others probably not, but one important part for research in universities in Europe is linked to programs funded by the European Commission. So right now we have what is called the 6G SNS, Software Network and Services Joint Undertaking. So this is let's say, a program that has the target to reach to the specification of 6G by 2030. And in this program, let's say, Commission has invested, or is investing significant amount of money, is in the order of 900 million euros that are put from the Commission And then this is a joint undertaking, this is a partnership with industry. So there is also 900 million euros that are put by companies that are participating in the program. So in the context of this program already started first call in 2022. There were the first set of projects that were awarded. And here I mentioned BERGE project. This is a project that is coordinated by Universitat Politècnica Catalunya and is related to AI-powered evolution towards open and secure edge architecture. So in BERGE, you are a group of 15 partners with academia, research, and industry. From academia, besides Universitat Politècnica Catalunya, we have Barcelona Supercomputing Center and the Center for Telecommunications from Catalonia. You also have University of Oulu from Finland and King's College from London. And then we have, as industry, we have participation from Ericsson, both from Sweden and from Turkey. There is also participation by Samsung, Intel, GTSI, and we have also Turkcell as a Turkish operator participating in the project. Then in this project, we have two main use cases. One is, let's say, around autonomous tram. Here we have GTSI that is deploying an autonomous tram in the city of Florence in Italy. And this is an area where it can benefit very much from implementing edge computing capabilities for the type of, let's say, services that they are exploiting, for example, obstacle detection. And then we also have another use case that is around extended reality and co-design of applications dealing with extended reality. In this case, the plan is that we have Arçelik is a Turkish manufacturer, and the idea is that we can have two distinct teams, design teams, in two remote factories, and then through the, let's say, extended reality applications, they are able to design, for example, a fridge or whatever of the household appliances that Arçelik develops. So in this research project, we have like three main pillars. One is Edge for AI, so designing the edge platforms that can be suitable to support AI applications and mechanisms. Then we have AI for edge. This means the models, AI models that will be useful to make the control and management of the 5G network. And here, for example, is where we can find application of some of these algorithms. For example, algorithm Irene has explaining about capacity sharing could be readily applicable in the context of this BERT system architecture. And then another important, let's say, building block in BERT is security, privacy, and trustworthiness for AI. And this is something that Irene has not emphasized much in the talk, but it's really important for the successful, let's say, deployment of AI mechanisms for the management and optimization of 5G networks. That is, that these solutions need to be trustworthy. So it means with that mobile network operators, let's say, won't be much willing to deploy a solution that is automatically taking decisions or changing parameters or configurations of the networks unless, let's say, he can rely that these solutions will perform as expected. So trustworthiness is important keyword for the future. Another research project that is also in the context of this SNS program is Big Green. In this case, let's say our group at UPC, we are participants, we are partners in this consortium, and this project makes a lot of emphasis on, let's say, energy efficiency and sustainability in 5G and beyond networks. So Big Green is exploring, let's say, how energy can be saved on all layers from the network, And here you can have in this picture, let's say, an outline of the, let's say, architecture that they are considering. And you can recognize here this Open RAN architecture that Irene mentioned before. And the intelligence planes that is developed in Big Green will be, let's say, supported by many, let's say, AI-based mechanisms. So again, we'll have like mechanisms, for example, that can support in intelligently switching on off the base stations. And with this, let's say, we can expect, let's say, substantial improvements and, let's say, contributions toward more sustainable future mobile networks. Also, besides, let's say, the research programs that we have at European level, in each country, then we have also our national funding agencies that support research. So in our case, in Spain, we have different programs also that universities can apply for funding. Recently, we had this, let's say, recovery funds that has also been supported by the European Commission in order to overcome the effects of the COVID-19. And there has been, let's say, funds that have been flowing towards the different member states. And part of these funds are being applied to, let's say, improve, let's say, research skills and developments, not only in universities, but also in companies. One of these examples is this Optimize project, this optimizational service platform for advanced 5G, 6G services. So the idea here is that we are developing a platform that can be offered as a service. This platform could be distributed, so there could be implementations of these platforms in different venues, companies or universities. And from this platform, you can also, let's say, deploy artificial intelligence-based mechanisms to support different aspects of the network planning, deployment, and operation. And for example, in this case, we have in this project Telefónica participating, and we are developing some of these solutions, like you can, for example, predict that you want to make some changes in the transport network of the operator, and you will have here the support of network digital twin, so that you can, let's say, anticipate what will be the impact of these networks in the changes of this are going to be predicted before you implement, let's say, the change. So if you can forecast somehow what will be the effects on the network, and then you can check, monitor, and this is acceptable or fine with the operator, then you can, let's say, move on and conduct these, let's say, changes or upgrades into the network infrastructure. Another project that is also linked to this national research agency is ARTIST. This is smart radio access with integration of user devices. So in this project, we are seeing that one of the important aspects of 5G is to make sure that you provide, let's say, ubiquitous coverage. You may know that one of the elements in 5G is that it's expected that you can exploit, let's say, higher frequency bands, and there you can face, let's say, coverage issues in these bands, and then maybe you can have so nice 5G technology, but of course, you don't have coverage, this is worth for nothing. So in this context, one of the elements that we are studying is to, let's say, revamp the concept of relaying, so the operator could deploy relays to, let's say, try to cope with these coverage holes. And again here, artificial intelligence plays a role, because you can have like AI-based mechanisms in order to automatically identify where you will have these coverage holes within your service area, and also automatically identify what will be the suitable locations for these relays, and then automatically, let's say, switch on and off these relays when needed according to the services.
Can I have a question between?
Of course, yeah.
So it's about the previous two slides, previous one. In fact, I see that how we can relate these two. So optimization, is it something like generally we see platform as a service?
Yes.
Or, right. So are we saying that we are going to optimize either the radio resources or some kind of resources in a distributed manner rather than doing it individually at every particular service provider or at every individual network? So are we taking it through cloud?
Yeah, the point in this, let's say, project, Optimize, there is a consortium of companies. And as I said before, we have, let's say, Telefónica's main operator in Spain. And then you can say you can have an ecosystem of companies around that can provide optimization services. And then we are foreseeing here that in this platform, in a distributed manner, you could have different providers providing solutions to optimize or to plan different aspects of the network, and you can rely on the solutions that are provided to this company, from these companies, to, let's say, implement this on, for example, Telefónica's network.
And the smart devices, is it again the similar thing? So are we going to monitor or manage the radio access? Like? You mean in context of this other project? Yeah. And in this, again, you could have like automated mechanisms that can enable you to identify where you have coverage holes in your network. And here we are also studying somehow more futuristic terms, because these, let's say, relays could be, let's say, the handhelds themselves. So we are seeing here that there will be, let's say, possibility that maybe, for example, from moving from, you are in a university and you are in a classroom and you have, let's say, for example, macro cell outdoors and you don't have good indoor coverage, and then maybe through one of these terminals you can make relaying and extend the coverage indoors, for example. Or if you are in millimeter waves outdoors, there can be some elements blocking into the area. You can get with your car, you are parking your car, you have a 5G modem there, and you are useful to overcome this blockage, and you could rely on this terminal in order to incorporate this as if it were another element of your network. And then you, let's say, can, let's say, get the support from this terminal to provide service to other terminals. But of course, this embraces many challenges, not only, let's say, technical, but also from the user's perspective. For example, how you engage your customers so they are willing to be part of this extension of the network. But these are one of the aspects we are analyzing. Sometimes this will be across the protocols and layers?
Yeah.
L2 or L3?
Yeah. This, let's say, for example, in this project, we have now recent publication in Vehicular Technology magazine, where we made the analysis on how this will affect at, let's say, protocol level, and we designed it, let's say, at different layers, what would be the adaptations and extensions that would be required so that this could be implementable. There are different options, but we made the analysis, and at least you see that from technical point of view, this is something that is feasible. As I said, another thing is for, let's say, business perspective, how, let's say, you can engage the users into this issue, but there are also motivations for the operators, because somehow, let's say, you can exploit your own customers in order to improve your own coverage footprint.
Thank you.
Okay, welcome. Okay, and last, I would like to mention this is a project will be just very recently starting. It's a trainer 6G towards trustworthy AI native radio access networks for the 6G era. And in this project, we have like three, let's say, starting hypotheses that also Irene, during her talk, has been emphasizing some of them, but it's just for considerations looking to the future, and probably this is connected to some of the questions we had in the previous section. So in the view we have in this project, national project, we start by the consideration that 6G radio access network will be AI native. Second will be that AI solutions should be trustworthy, as I said before. If not, it will be difficult. That will have widespread deployment of AI solutions in networks. And then that network digital twins will be key enabler for this trustworthy AI native 6G RAN. This means that for, let's say, the analysis, development, and assessment of these AI solutions, you need to rely with this type of mechanisms, like it is a network digital twin, to support the training and, of this type of aspects before you can move towards deployment of the network. So with this, I will let Irene to wrap up with kind of concluding remarks.
So thank you, Oriol, for all this concept. So now, just to finalize this tutorial, I will just conclude with everything that we have covered during these 2-3 hours. So first, I introduced what was the role of AI and machine learning to deal with the complexity of the management that we have in 5G and beyond networks, including what is the standards perspective. Also covered what I gave an overview of the different machine learning algorithms, putting emphasis on reinforcement learning, explaining the different elements that we have in reinforcement learning, and also analyzing what is the potential of reinforcement learning to deal with radio access management problems. Also, we saw that this can be applied into different time granularities and associated to different control loops, to which I provided some examples with capacity and coverage optimization, admission control, and max scheduling. So, and then I covered what are the different stages that are involved from the design till the production of the reinforcement learning solutions for the RAN. In this design stage, it was relevant to define what is the problem, and also it's relevant to consider what are the available parameters by standardization bodies, both for configuring and also to obtain radio access management parameters. Also, we covered the development stage, including the coding of these solutions based on different libraries, and also what was the role of the network digital twin to perform all this training in a realistic environment. And finally, the production stage, in which it's important to prepare the solution to be deployed in a production environment, including the management of reinforcement learning solutions during the training and the inference in the ORAN machine learning framework, and the need of developing these standardized interfaces like O1, the E2, and A1 for these solutions to be integrated in the network. Also, the need to containerize these solutions to be able to package them and to deploy them in a production environment. Then we showcase this by showing a specific solution, that is the capacity sharing solution for RAN slicing. That was the approach by a multi-agent reinforcement learning solution where the different agents use the DeepQ network algorithm. The solution is compliant with the ORAN and 3GPP parameters. And also we show the software that we developed for this solution, the structure of this software for you to have an idea of how this would look like. And also we showed how, after training the solution, what is the behavior. Also, that we specified a network digital twin for this solution, and finally, what we did to prepare this solution to deploy it, and we also showed some elements of this implementation. And finally, Uriol has covered the contextualization of the solution and also of our research in general in the Verge, Big Green, Optimized Artist and Trainer 6G projects. So we hope you have, well, here you have some key bibliography for this presentation, including reinforcement learning also. And well, we hope that you have enjoyed and that this presentation has been useful for you, and at least you have a new perspective of how this AI and specifically reinforcement learning may have on networks. So thank you very much.
Any questions for both the speakers?
So I have a question from the professor. So he has given very wonderful information related to how the people in the Europe, they usually do the research, especially with the collaboration with the academia and the industry. So, and you people are wonderfully doing with the 5 different projects in the different areas of the network, especially 5G and using the IML. So now only thing is, can we collaborate this university with your team, as you are a very good team with the industry, academia and partnership, how we can get the help, support, or to learn different aspects to implement the 5G in our place?
On our side, I mean, our group as academic, you are always open to collaboration. We keep very, let's say, open-minded attitude with everyone. So we are happy to discuss with anybody, and if we find topics of common interest and, let's say, possibilities for collaboration, we'll be happy to do that. Besides this, let's say, aspect of more willingness, I know that, I don't know if now, but in the past there has been, like, there are some programs that have collaboration. So in context of European projects, for example, there are, in this last call, there was Euro-Korea and Euro-US. And so there are frameworks that more, let's say, these are aspects that, let's say, are discussed more at, let's say, political level, but they establish, let's say, regional collaborations. And there are European projects where they are open to collaborate with a specific region. So
yes, Indian government also have signed some collaboration, and they have different projects in the European countries with the academies. So they also call for the proposal for the projects. In the England itself, they one, I think one unit is there, I forget the name. So based on that, we get some information or somehow collaborate, we discuss with the other things also. We will definitely like to do this.
Of course, I mean, one thing is, let's say, you can have interest, but if you have, let's say, a framework that allows you to provide some support, some funding and exchange, of course, this makes things much easier. Yes. But we'll be happy to discuss.
Thank you, thank you.
Any other question?
Okay.
Thank you. May I request Dr. Shamal Banerjee, Dean, School of Basic Sciences and Research, to felicitate the guest. Let's proceed with the third tutorial, which is the last one for this day. The next tutorial is on innovative techniques in medical image storage, transfer, and compression using wireless communication. So I'm delighted to introduce our expert for the next tutorial, Dr. Ashok Kumar, Dr. Ashok Kumar is head of Sharda Next in Cyber and Quantum System Facility and Center for Artificial Intelligence in Medicine, Imaging and Forensics, Sharda University. He is also professor of physics in School of Basic Sciences and Research. He has obtained his master's in physics from IIT Kanpur and PhD from Johns Hopkins University, USA. He has a postdoctoral experience at Stanford University in microfluids and from Massachusetts General Hospital jointly with Harvard Medical School in medical imaging. Dr. Kumar was awarded with the US National Science Foundation's Antarctica Service Medal of USA. He has also worked in biomedical instrumentation industry. Currently, his research involves applications of artificial intelligence in medicine, medical imaging, medical acoustics, speech and handwriting forensics, space physics, molecular dynamics, and quantum machine learning. So, sir, we are on to have you for this tutorial. May I request Dr. Shyamal Banerjee to welcome the guest speaker. So you may begin the session. USB है? ये किसका है? ये तो उसके लिए स्लाइड
इसको डिस्टर्ब कर दो। Good afternoon. Thank you for being here at this late hour. I really appreciate all of you being here. And this tutorial is about medical images and different medical image modalities, their storage, transfer, compression, and what kind of challenges they present, especially dealing with communication of these images. So since this is a tutorial, I'll also be dealing initially with modalities of medical imaging and what kind of issues arise there. And then I'll come to different topics, including compression, transfer, storage, and all that. And if I have some time remaining, I'll talk about AI-related medical imaging issues. So common medical imaging modalities, many of you already probably know by experience, are magnetic resonance imaging, computed tomography, X-rays, ultrasound, PET, which is positron emission tomography, SPECT, single photon emission tomography, and sometimes optical imaging is included. Doppler imaging is also included, Doppler color imaging. So there are several kinds of medical imaging modalities. And they involve different kinds and different amounts of data that needs to be dealt with. So I'll initially start with introduction of these different imaging modalities and what they do and what kind of data they acquire and how do we deal with it as far as storage and communication, et cetera, are concerned. MRI, many of you know, is basically built upon a magnet which is a quite powerful magnet. Human MRI machines come in 1.5 Tesla basic magnet, 3 Tesla, or 7 Tesla. 1.5 Tesla machines used to be very common in old times. Nowadays, 3 Tesla has become standard, and 7 Tesla is becoming quite common nowadays too. Higher the magnetic field strength, there are some advantages gained, but also cost goes up a lot. Now, MR modalities are famous for imaging soft tissue. Like X-rays are good for imaging bones, but soft tissue is best imaged using MRI. And by the way, we know that last year's or this year's Nobel Prizes went to AI people, both in chemistry and physics. And in this biomedical imaging domain also, physicists have received Nobel Prizes before. For MRI also, Nobel Prize was given in physics earlier. Now, there are many, many MRI modalities. Let's discuss about that. We think that those who are not very familiar with MRI, they may think there is just one kind of MRI image, but there are many. Most basic MR contrasts are given by T1 and T2 imaging. This comes from NMR days. Those who are in chemistry or biochemistry, they will know about it. There's some relaxation which happens in nuclear spins, and that happens at different rates because of two different mechanisms. One leads to T1 relaxation, one leads to T2 relaxation. So T1, T2 images are some of the basic ones. Then we have many more variations. Flare images, one more. Then diffusion-weighted images, which are related to diffusion of water through the tissue. So, brain tissue is not isotropic. It is highly anisotropic because of presence of white matter fiber tracts. So diffusion does not happen isotropically in all directions. So diffusion is not describable by a single scalar number inside the brain. It is described by a tensor. So when we have to determine this full diffusion tensor of water molecules inside the brain, we need several directions of imaging. I'll talk about that just a little bit. As I told you that in MR machine, there is a single big bore. Along the axis of the bore, this stable, strong magnetic field is present. But there are several other coils present that are called gradient coils. And these gradient coils can apply magnetic field gradients in X, Y, and Z directions. And by suitable combinations of all these gradients, we can really apply gradient in any direction. We have 3 components available, so we can do that in any direction. Apart from these gradient coils, we have some radio frequency coils that are resonant to MR or NMR frequency of water molecule. Mostly water is imaged, rather protons, because water molecules have protons, and proton NMR frequency is the one which is mostly used in MRI. But in MR spectroscopy, other nuclei are also used. So basically, we are looking at protons as magnets because they have spin and they have a magnetic moment. When we put anything inside this magnetic machine, MRI machine, all the protons align along the field. And then a radio frequency coil, which can be a body coil, head coil that we put on the patient or subject, sends a pulse of radio frequency which disturbs the spins. And they lose their alignment, they start spinning, and they can even go almost orthogonal to the main field or even reverse if we give it enough time. And then we'll let it go. And after that, these spins that are spinning, which are not anymore along the field, they start relaxing. Relaxation happens by 2 mechanisms, T1 and T2, as I told. T1 mechanism is just recovery of the main axial field, and T2 is decoherence of the several spins within a certain voxel. Voxel is what? 3D correspondence of a 2D pixel of an image. Most of the medical images are 3D. Simple X-rays are not, but CTs are, MRI is. And we have voxels, 3D picture elements. And inside a voxel, which can be macroscopic size, millimeters, you can have a very large number of protons. So when they start relaxing, they're not always rotating together. Because of tissue non-uniformities within the voxel, they lose coherence, and because of that also, this recovery is affected. And that relaxation is called T2. So as I told you, these are the 2 main mechanisms. Then we have flare, which suppresses the fluid. There are diffusion tensor imaging, as I told you about diffusion. There is a MRA angiography. There is a perfusion weighted imaging. There is a functional imaging, which measures functional activity within the brain. And dimensionality of data changes. A single X-ray radiograph is two-dimensional. But a single T1, T2 image is three-dimensional. A diffusion tensor imaging uses multiple directions of gradients, so get diffusion in different directions to determine the whole tensor. So it can be at least 6-directional or more. Actually, high angular resolution diffusion imaging can use 256 directions of gradients also. So you have so many separate images within one MR scan. In functional imaging, brain is rapidly being imaged over time to figure out what kind of activity is going on in the brain. You can have several 3D acquisitions within a certain period of time. So size of data in MR or medical imaging can be huge. In a single protocol can be a few megabytes to gigabytes. And typically in a certain one particular acquisition, you run several protocols. The amount of data gathered becomes huge. And that leads to storage and transmission related issues, as I was discussing. I already discussed what I mean by T1 imaging. It's a T1 relaxation happens because protons align with the main magnetic field and axial field is recovered at a certain rate. And this rate of relaxation depends on the tissue in which this proton is being found. Different tissues have different relaxation rate. Gray matter has different than white matter. Cerebrospinal fluid has different. So this leads to tissue contrast, and that's what is seen in these images. T1 images show gray matter is gray, white matter is white, and fluid is dark. So they look pretty nice to us because we expect gray matter in the brain to look gray. T2 image, on the other hand, shows loss of decoherence of spins as they are recovering. And here, the fluid appears white, as in the central image you can see. Central image is a simple T2 image. Gray matter appears slightly grayish, and white matter appears darker gray. Somewhat inverse kind of thing with T1 images. There is another version of T2 on the right-hand side called flare imaging, fluid-related inversion recovery. What it does is, it actually suppresses the signal from the fluid, so all this white part, which is because the fluid in the brain is suppressed out. Flare images also can be slightly larger than other images. Sometimes to figure out certain problems inside body, for example, here you can see a tumor. On the left-hand side, there is a simple T1 image. If you look carefully, you may see some deformity happening in that part, but it's not so clear. What we do, we can inject, while a person is being scanned, a paramagnetic substance, usually gadolinium. And while it is being injected and going through the blood vessels, also going into the brain, and gadolinium passes through the brain into the, remember, there is a blood-brain barrier. So normally, blood does not go into the brain tissue. It's all in the surrounding part of the brain and supplies nutrients to it. But gadolinium can cross. And it can be there in that part. And if, for example, in a tumor, it can lead to enhancements because it's a paramagnetic substance. If it is held there for some time, it will lead to brightening. You can see the tumor is highly brightened there. These are different kinds of methods people use. Diffusion tensor imaging, as I told you, can lead to large amounts of data. Brain is anisotropic, so full diffusion tensor is involved. That means it's a symmetric 3x3 tensor. So there are 6 independent components. That means you need at least 6 gradient directions to determine this tensor completely. And once this tensor is determined, we can find many, many different properties. We can find average of all the eigenvalues, which gives average diffusivity. Then we can find fractional anisotropy in that region. And there are several other measures, radial diffusivity, axial diffusivity, and all those kinds of things. But more so, we can color code each voxel of the image by the anisotropy direction of this. Tensors, 3-dimensional tensors, can be represented geometrically by an ellipsoid. And the biggest eigenvector or eigenvalue shows a direction where diffusion is most prominent. So using that, we can color code a diffusion DTI image by showing 3 different directions. RGB encode the 3 different directions, up, down, left, right, and front ventral. So this color coding is done that, and this shows the direction of white matter fiber tracks, because white matter fiber tracks are the ones that are anisotropic. Gray matter is mostly isotropic, and gray matter is where the computation happens on the surface of the cortex. White matter fibers are the wiring of the brain that are like wires, and they have high anisotropy, and that's where we see all this diffusion tensor anisotropy coming up, and orientation of fibers is shown here color-coded. Now, using this diffusion tensor imaging, and especially if we use even HARDI, it is called high angular resolution diffusion imaging, where we can use not just 6 directions of gradients, but maybe hundreds, 256 directions also people use sometimes. What it does, it gives unprecedented accuracy about the direction, and also if the fiber crossings are happening, the diffusion tensor can get confused. It can think, oh, how do I make my ellipsoid if I have a fiber crossing in a certain voxel? It will make something which is isotropic there, which it should not. So in those cases, this high angular resolution imaging helps. When we do this imaging, we can use the eigenvalues and eigenvectors in each voxel to track from voxel to voxel how the white matter fiber tract is moving through the brain. So this is called fiber tractography. And we can generate these kinds of images. On the right-hand side, you can see a surface model of the cortex. On the left-hand side, you see the fiber tracts that have been generated using high angular resolution diffusion tensor imaging. And as you can see, there are so many directions used, each of which correspond to a separate MR image. The data amount is quite huge. Next very important MR modality is called functional MRI. Functional MRI comes from so-called BOLD construct, B-O-L-D. BOLD stands for blood oxygenation level dependent contrast. What happens is that if a certain part of the brain becomes active, blood supply to that part of the brain momentarily dips and then rises, because that part of the brain is now doing a lot more calculations and needs more blood, more nutrition. So blood supply increases, then it falls again. This is a typical hemodynamic response, or also called blood oxygenation level dependent response, called BOLD signal. So this way we can actually measure activity in the brain in real time. Suppose you put a subject inside MRI machine, you give them some kind of stimulus, auditory, visual, tactile, whatever kind of stimulus, and you can do their functional MR imaging. You will see that part of brain become active, which corresponds to either auditory, either visual or tactile, or whichever part which it corresponds to. So it allows you to monitor real-time action in the brain. It's not some, We can also give certain protocols that person has to follow during the imaging, and lots of cognitive studies are being done using functional MRI, apart from clinical studies. So this is a very important imaging modality. But what happens here is that you are acquiring 3D images rapidly over time, many times. You apply a full 3D image, then again a 3D image, again a 3D image, and you do that very quickly over whatever time the protocol lasts, maybe a minute or several minutes. And that can accumulate lots of images, and these functional images can be huge in size. The processing also requires a lot of work and generates a lot more images. The whole thing can be quite big, several gigabytes by the time you're done with them. In the left-hand side, you can see there's a neurovascular connection. Neurons are connected with blood vessels. As I said, blood vessels do not go into the brain, but they have to supply nutrients, which leads to this hemodynamic response. And at the bottom graph, what you see, you can see there is a square wave kind of thing there. Okay, at the bottom you can see the square wave, which is basically a stimulus that we are presented to a person. Suppose I'm wanting to study whether the visual cortex is working or not. I'll turn on lights, turn them off, turn them on, turn them off. And then I look in the brain. In the time series of each voxel in the brain, I do a correlation with the original stimulus waveform, which is a square wave in this case. And in whichever voxel I find a good correlation, I'll tell that that voxel was responding to this stimulus. And that's how we figure out which part of the brain is active to that stimulus, and that's how we figure out which part of the brain does what in certain ways, especially to sensory stimuli. Functional imaging is also nowadays being used not in with sensory stimuli, but a new discovery, not so new discovery, a couple of decades ago. It's called resting state fMRI. You put the person in the MRI machine, ask them to close their eyes and relax. No stimulus being given, just image the brain. This discovery led to something called so-called default mode network of the brain. When we are relaxed, no sensory inputs are coming in, our brain develops a certain strong activity, a network becomes active, which is called default mode network. People have associated it with different things, including our sense of self. And this also is a good indicator of whether something is right or wrong with the brain or not. So nowadays, resting state fMRI is also routinely being acquired. X-ray CT, people are quite familiar with. X-ray image on the right, you can see this is related to normal X-ray and COVID X-ray. X-ray images are small in size, 2D, but if you have a large film, and if you digitize the film, they can still be quite large, several megabytes, tens of megabytes. CT images are again three-dimensional. This is computed tomography, based on X-rays only, but instead of one source and one sensor, you have a circular array of sensors and sources, which basically use a so-called radon transform to generate the 3D image from line integrals of all these attenuations in all the directions. Now, CT images also come in a couple of varieties. There is something called HRCT, high resolution CT image, which can have very, very high resolution in the plane, which gives a very good resolution in plane, much higher compared to MR, but it can also lead to increase in size. Now, medical images are stored in a certain format. The DICOM format is the most universally accepted format for storage and transmission of medical images. DICOM stands for Digital Imaging and Communication in Medicine image format. All medical scanners, whether MR, CT, PET, SPECT, all of them basically output the images. They can have a raw format image, but eventually they output them in DICOM format. And DICOM format is what is used for storage and transmission. When we do research, we also get DICOM images from all these machines, but then we usually convert them to some other formats, like NIFTY format and this format. But DICOM is what doctors and medical devices and hospitals deal with when they are dealing with medical images. DICOM also is very, very nice format in the sense that it takes care of communication as well as storage, as well as you have archiving. DICOM typically interacts with so-called PAX system. PAX system is where archiving and interaction of data happens. DICOM images also store a lot of information in the DICOM header. Normally, we are used to JPEG or PNG, these kinds of raster images of 2D kind, where the header basically keeps some basic information about number of rows, number of columns, number of bits used to encode each particular pixel, and some other information. But DICOM images, on the other hand, can store a large amount of information. They store patient's name, age, hospital information, the ID, time of scan, and series of scan, all kinds of detailed information about the patient, about the machine on which the scan is being done, about the acquisition that is going on, what kind of acquisition it is. So from the DICOM header, lots of information can be stored. So it's not just imaging data that is being stored in a DICOM file. It's a standardized file format. It has also its communication protocol, interoperability. As I said, all medical devices, imaging devices, use DICOM format to send images or even store images. Hierarchical data structure. As I said, it can have a patient study, series, image. So for a single patient, we can track several visits of the patient, several studies for that patient in the same visit, or different kinds of modalities. Maybe he had X-ray, maybe he had CT sometime, maybe MRI. All of this can be tracked together. So that makes things very convenient. Especially when we store this in PACS system, we can retrieve the data easily, quickly, and reliably. And that's also not only good for doctors when they have to treat patients, but also for research where we can do retrospective studies by giving some search parameters, and we can quickly find relevant data there using this. All of you who have stored hundreds of PDFs in one folder knows the problem of how to deal with this kind of thing. We keep on searching where is that PDF hiding, which we want to look for. So this kind of organization helps doctors a lot because a lot of imaging data is coming in, and retrieval and transfer, archiving, storage becomes much more easy this way. The system for archiving especially is called PACS. It is Picture Archiving and Communication System. It deals with DICOM files. It has archive. It can be cloud storage also. It has a firewall, communication, all kinds of things it deals with. It can also deal with two important information systems that hospitals typically have: RIS, Radiology Information System, and HIS, Hospital Information System. Radiology departments have their own information systems to keep track of all the images they have. And hospital, when they keep track of who is registered, what the patient ID is, or whatever kind of things they do, that is kept in HIS. PACS can interact with both of them. PACS system, image acquisition, storage, viewing, transmission, and it can also now be, as I said, it is very helpful for research also, and for AI-related work using medical imaging, which is one of the dominant themes in AI. It has been at least in the last couple of decades. Medical applications of AI have been huge. Generative AI has taken over the imagination of people in the last couple of years, but before that, most of the applications of AI were successful applications were in medicine. Cloud-based PACS and all this kind. Future PACS is also very can be useful for future growth of medical data handling, storage, and all that. Especially when new communication protocols are coming up, like 6G and 5G. Typical DICOM file sizes for different imaging modalities. As I mentioned, files can be a few megabytes to gigabytes. And that's just single protocol. In a single study, we can have several such acquisitions, and that increases the file size by a large amount. I have listed here several imaging modalities. MR spectroscopy is also there. There is MR angiography, the CT angiography, MR angiography, and there is another called ASL, arterial spleen labeling. There are many such things. Perfusion-weighted imaging, where we can, again, inject contrast agent in the blood, and then we image and see which part of the blood vessels in the body are slow or have been damaged or in making the blood flow through them. Now, medical image compression, since image sizes are large, increasing, medical scanners like MR and CT are becoming much more common. Imaging is also becoming much more common because nowadays doctors go by so-called evidence-based medicine. As insurance, previously we didn't used to have medical insurance in this country as prevalent as it is now. But with the advent of insurance and with our increased medical facilities, this evidence-based medicine has become much more prominent, where doctors like to see the evidence first before writing any medications. I think all of us in India at least are used to, when we used to go to a doctor, he would write the medicine right away, right, without any investigation. But nowadays, doctors hesitate to do so. And because of that, imaging, amounts of imaging has gone up a lot. Many hospitals are buying multiple scanners and new scanners all the time. Even Sharda Hospital has 2 MRI scanners, 2 CT scanners, so, and 1 CBCT in dental school. So this is the trend of the future also. So compression is required, and it will be very helpful when we want to deal with large amounts of data, especially if you have some real-time kind of applications. Now, types of compression techniques, I think most of us know basic compression techniques like JPEG. And loss compression can be 2 types. I think this is basic, but since it is tutorial, I was included this here. Lossless and lossy compression. Lossless compression is where we can reduce the size of an image without actually losing any information. It is possible to do that because large parts of image may have some repeated information which can be somehow encoded differently to reduce the size. And there is another lossy compression where actually some information is lost during the compression, but compression ratios can be larger, that we can reduce the size of the file much more than in a lossless compression. JPEG is one of the most common lossy compression methods. JPEG 2000 and a 3D JPEG 2000 is also becoming popular nowadays. 3D JPEG 2000 is suitable for 3D medical images. And it also allows for AI integration much more. I'll come to that in a bit. Where advanced compression methods are wavelet-based or AI-based. AI-based compression methods are becoming, they are catching people's eye nowadays because we can do some deep learning kind of model which actually reduces the sizes of the files while keeping high amount of diagnosis-related information within those files. Those of you who are probably familiar with AI a little bit, we know that there is an autoencoder kind of architecture used widely, where at the input layer we can give certain amount of information, but as we progress through the layers, we reduce the size of number of neurons. So we are actually compressing it, or rather we call it, we are encoding it into a smaller number of bits or numbers. All the embeddings that we have in NLP and LLMs, all those things we are hearing quite nowadays in ChatGPT, they also use this kind of method. So AI-based compression is also quite important nowadays, and it can be done, and it can achieve very good compression ratios while not losing medical information or diagnostic-related information too much. Because medical imaging is very sensitive. It has to deal with life of a person, so we cannot be careless here. So we have to use methods of compression which do not lose important information. Then hybrid compression methods are also applicable, where lossy and lossless can be combined together. And for example, suppose there is a tumor inside a part of the brain, that is where we are interested in. So there we can apply a lossless compression method that in that particular region of interest, but in rest of the image we can use a lossy compression. So these kinds of strategies can be applied to make the size of the image smaller. I'm giving an example of AI in compression, one example. This was 4D DTI images. Why 4D? As I told you, diffusion tensor imaging requires multiple acquisitions of MR images. So this extra dimension is dimension related to multiple directions. And this can have at least 6 or up to 256 even directions. So this 4D has so many extra points there. So these are 4D diffusion tensor imaging data. They're large. And AI-based methods can reduce file size by up to 70% with no diagnostic quality loss. So I'm just giving some example. I'm not saying that this is the best that is there, or it can always happen, but what is possible. Another is using 3D JPEG 2000 shows CT strength at 15:1 compression. So this is another method where in packs 15:1 compression was obtained using 3D JPEG 2000. There are several different compression algorithms. I've just listed them here from this particular paper. I don't need to go over them, all of them, but we need to know that this is a very active area of research. A lot of people are working, because in our world, the data creating machinery, devices are increasing in number, and typical data is also increasing in size. We used to have very small, few pixel cameras in old days. Nowadays, all the number of pixels is going up. Everyone is acquiring these images, number of cameras, this medical devices. So data is being generated in a large amount. And this data also goes through in networks. And networks have to handle this kind of data flow. So compression will always be a very hot commodity. So new algorithms and new approaches are always going to be there, and they're always very welcome. There are some other methods here, wavelet-based, some other based methods. Now, digital communications are, of course, there in healthcare a lot. What about wireless communications? Wireless communications can support telemedicine and remote consultations. They can enable Internet of Medical Things, IoMT or MIoT. There are a couple of terms people use here. IoT, as we know, is Internet of Things. We used to have Internet of Machines, then Internet of Things, then Internet of People, the social media. Where ordinary devices are connected to Internet, we call them Internet of Things. When medical devices are connected, this is a medical Internet of Things, MIoT or IoMT, Internet of Medical Things, for patient monitoring. And this can facilitate real-time sharing of large medical imaging data sets. People, especially in countries where medical care is not very common, ratio of doctors to people in India is much lower than, let's say, USA. And access to very good quality care is not as widespread in India, for example, in many other countries, and especially in remote and underprivileged areas. And remote telemedicine can help provide very good health care. And if this telemedicine has to be real time, it doesn't have to be real time all the time, but in some cases, for example, especially in robotic surgery, or someone is in trauma or some emergency case, someone is having a stroke and a doctor sitting far away has to make a judgment and give a diagnostic or some advice right away. In those cases, communication and speed of communication becomes very, very important. And so for telemedicine, remote consultations, and wireless communication can enable Internet of Medical Things, real-time sharing of large medical data sets, and common methodology we all know are Wi-Fi, 5G, and in future, 6G, which will be a total game changer. It's still in formation in many ways, and this conference, I'm sure, a lot of wise people will be talking a lot about it. Bluetooth, Zigbee, and different kinds of things. Portable imaging devices, continuous patient monitoring devices. So apart from digital communications, which is a superset, even wireless communications have a large role to play in many of these cases. Role of 5G and future wireless networks. 5G in healthcare advantages can be high bandwidth, ultra-low latency, network slicing, remote robotic surgeries. Robotic surgeries I've been hearing this word for a long time, and it has been performed in different places. It hasn't become so widespread because of many things. Technology is there and also trust issues there. But if there is a life-critical issue, someone has to do it, then if the facility is there, someone may want to use it. Robotic surgery will be very I think it's still a very challenging technology, and which will be a big thing for the future if it actually can work out seamlessly and becomes widespread. It would require high bandwidth, ultra-low latency, and network slicing and all that. Now, future trends, IOMT and 6G networks, as I said. And this conference, this is only the first day, and many people will be talking about 6G and what it can do, especially edge-based computing. So now, security concerns and solutions, data breaches, interception. Now, data breaches are always bad. We don't like our data to be breached. In medical cases, it also leads to a lot of liability for hospitals or doctors because there are certain regulations for patient privacy. In USA is HIPAA, HIPAA, the Health Insurance Portability and Accountability, which actually requires that all hospitals, all doctors, or even all researchers who deal with human data to be compliant of HIPAA. So if you do a research in USA, you have to be HIPAA compliant. You have to get ethical approval. Similarly, in Europe, we have GDPR. India also has requirements of privacy, which is natural. And when we are using wireless communications, or even other kinds of communications, the data breach can lead to a lot of liability for medical hospitals, institutions, doctors, if this kind of breach can happen. So this actually is a high priority area. It's not like my some homework was hacked. It's much more serious here. Now, solutions can be encryption, multi-factor authentication, and ensuring that whatever we do are compliant with HIPAA and GDPR kind of systems. I'm including last couple of slices on this particular topic about continuous monitoring, improved accessibility, and predictive maintenance that IoT can help with, which can connect imaging devices, storage systems, and diagnostic platforms to enable real-time data exchange. Now, edge computing in medical image management can be quite important. As I said, this privacy can be a big issue in medical images, and if data does not leave the locality where it is, then these issues are mitigated. So edge devices process and analyze images locally, ensuring faster diagnostics. Critical for point-of-care imaging and emergency scenarios, and reduces the amount of data transferred to central servers by processing images on the edge. So edge device itself is doing a lot of computation, heavy work. You don't have to transfer image to some other server where this computation analysis of data is being done and then some result being acquired. And enhanced privacy. Since the actual data, which may have patient identifiable information, does not leave the locality, it is much more safer that way. It's quite easy if you take MR image or even CT image, 3D CT image, MR image, to actually generate 3D facial profile of a person. So previously, we used to think that in DICOM images, if we raise the person's name and hospital and this and that, the identification marks, then we are okay. But actually, it turns out, by normal MR slices, we can generate the face of the person. So now, even in sharing MR images nowadays, the frontal face part is being erased. I noticed that Human Connectome project, which is a US-based project, consortium of many universities, which provide large amount of very good high-quality MR data for connectivity, brain connectivity studies. They also have initiated or implemented this. So patient privacy is always going to be a big issue, and edge-based devices help in that. Emerging synergies. Now, as I said, IoT and edge computing, we have already devices there locally, and edge computing can deal with them, do all the heavy work locally. reducing amount of data that has to be sent to central servers. AI and edge computing. We can implement AI. For example, nowadays, many times, when we train an AI model, we have to, for inferencing, we have to load it up on a server. And for example, ChatGPT. We log into ChatGPT, we send our prompt, and then it comes back with something. So actually, our message goes through the internet to that server, things happen there, and then it comes back to us. This is what it has been so far. But in the future, a lot of this heavy-duty AI inferencing can be done on the edge itself. And that will reduce, of course, amount of data transfer. It will help in privacy and all kinds of issues. So that IoT and edge computing and AI and edge computing are important emerging synergies that we can see in future, especially with 6G. How much time do we have, sir? Or if I have time, then I'll go on to AI. Otherwise, I'll stop here. Okay. I will now move the direction of the talk a little bit to artificial intelligence. And it's not going to be very heavy on artificial intelligence because I thought as a tutorial, I don't see many students right now, but it could have been useful for them. So I'll go a little fast over them. So, okay. But since AI is such a buzzword nowadays, it's probably a good idea, those who are not completely conversant with it, to get some overview. I'm not going to, AI is itself a big field. We cannot go into all the fundamentals, but at least have a good overview now. So I'll start with this quote from a professor of computer science at Stanford University, Fei-Fei Li. He says, as a technologist, I see how AI and the fourth industrial revolution will impact every aspect of people's lives. I think, I forget who said that AI is the new electricity. Now, everything we know in our life nowadays runs on electricity, right? My sound is reaching to you through electricity, light, whatever, computer. Everything is working on electricity. So AI will be the new electricity. Everything will be working with AI. So AI, actually, people used to say these things a couple of years ago, but I think ChatGPT has really hit people really hard and woken them up that, yeah, this could be, yes, this can be the case, that AI will be very, very important. And actually, there are quite diverse opinions. Professor Kremchutsky here thinks general intelligence is coming very soon. Some people think it's quite far and maybe very, very, very far. Maybe some people think it might be coming in 5 years, so we'll see. Well, we hope to live at least 5 years. Let's see. It's all in God's hands, but no. What is artificial intelligence? Artificial intelligence is basically machines behaving like humans. We humans have this hubris to think that we are intelligent, and we define intelligence by comparing with us. Actually, defining intelligence by itself is not so easy. Turing, the great man, himself defined intelligence by this comparison, which is called Turing's test. Basically, we put a person and an intelligent machine, let's say a computer, behind a curtain, interact with both of them through, let's say, a keyboard or some other device like that. We don't know whether we are interacting with a person or a machine, and if we cannot tell the difference by all our interaction, then we'll say that machine has passed the Turing test and machine is intelligent because humans are intelligent and we cannot tell the difference from humans. So measure of intelligence is human. And this is a workable definition anyway. So making machines behave or work or compute like humans is what is AI. It's intelligence of artificial kind. Turing, long time ago, in 1950s, gave the first ideas of how computing actually can work. There were no real computers to say worthwhile there. But he gave the initial, very, very root ideas how computing can actually happen, what it means to compute anything. The ideas like input, output, CPUs, internal states of CPU, memory, and actually finishing a computation, Turing's stopping problem, all those things arose from that. And we all know that he was the one who also broke the Enigma code of the Nazis during the World War. Died quite young, but quite a bright person. So his universal machine came in early 1936, but his ideas about AI started coming in 1950s. He wrote a paper, I think this paper, in 1950, where he asked this question, can machines think? And imitation game, all kinds of things that he started to do. I'm not going too much into history. Maculopets basically thought of gates, logic gates, as inspired by neurons, some simple operations like all we know in electrical engineering people, all we know what logic gates do. But these were actually inspired by biological things a long time ago. John von Neumann combined the ideas of Maculopets and Turing to come up with some kind of computing device, or he actually came up with an idea of what a computing device can be, and he actually proposed it in his book, Computer and the Brain, 1958. This is Alan Turing's. So this is what I say, what it means to be human or intelligent, okay. So this is the question. All of us are here. We think we know what a chair is, right? All of us think we know what a chair is, right? I will ask you, can you define a chair to me? Which will work in every possible case that you can find a chair. When you look at a chair, you will say, yes, it is a chair, but can you predefine it? Can you give all the features that will define for me a chair? You can look here some examples. There are some strange ones. When we look at them, we say, yes, these are chairs. And you can find many more such examples which will say, yes, this could be a chair. But if I ask you to give all the features which will define a chair for me, it will not be complete. Initial AI, especially this machine learning still does that. Machine learning, the traditional machine learning, does all its intelligent machine training based on features supplied by humans. We define the features. Suppose I have images of cats and dogs and I want to differentiate cats from dogs. I will say, oh, this means to be a cat, and these features define a dog. But you can always find a cat or dog which will not fit those features. There is always something like that. But there is something in our brains, right? When we look at a cat, we usually find that, yeah, it is a cat, even though it did not fit our predefined set of features. So our mind works deeper than that. Initial AI failed, earlier AI, even though a lot of bright people worked with it, because it was trying to do things top-down. It was later realized that biologically inspired architecture is the way to go. Artificial neurons, perceptrons, then artificial neural networks, and then 80s, this feed-forward backpropagation algorithm success led to at least theoretical ideas that things can work. Hardware was not there, and related software developments were also not there, so it did not take off for a while. But in past decade or 2 decades, another big revolution which has happened called deep learning. Deep learning is what our minds, it comes close to what humans do. Traditional machine learning requires you to provide features of your data so that it can do some tasks like classification or other kinds of tasks. Deep learning does not require you to give any features. It just needs large number of examples. It's like babies. When a mother trains a baby, oh, this is a cat, this is a cow, this is a bus, she does not tell bus means to have this, or cow has this. It just points, this is cat, this is dog. And then the child says, okay, this donkey is a dog. She says, no, you're wrong. This is all a mom has to do. She does not have to define features of a donkey or a cat or dog. She has to just keep on correcting the person, the baby. This is what deep learning does. You just need large number of examples, and you just need, at the end, to tell whether you're correct or not correct. This is called supervised learning, deep learning. Features are extracted by initial layers of the network directly, and those features are then used for classification, regression, or any kind of other task that you want. This is for supervised learning only. perceptron simplified neurons, probably all of us know that this is what one major biologically inspired growth that happened, which led to successes of AI. And one of the major things that happened here is this S kind of thing, sigmoidal activation function, that addition of signals coming from the left, x1, x2, xn, and all that, sigma adds all of them multiplying by weights. This is just linear algebra. This sigmoid function adds a nonlinearity to it. And that turns out to be extremely important for training neural networks. Without this nonlinearity, things do not work. So this is also present in biological neural networks, and this we had to include in actual artificial neural networks for them to be able to learn. So all activation functions that we use within the internal layers of neural networks are nonlinear. They don't have to be sigmoid. We have ReLU kind of things, but they have to be nonlinear. Linear activation functions are used only at the output layer for regression kind of tasks. Neural network can, a simple neural network which is fully connected can with this. You have input layer of neurons, then next layer, then next layer, then next layer, all of them connected to all of them layer-wise. This is the usual feed-forward network. And at the final layer, you have some outputs. If output is wrong, we generate a loss signal. Then you propagate this loss or error backwards in a error back propagation method. Basically say, I got this much error. Who is to blame? So this output layer neurons blame the previous layer neurons. And whichever had the larger weight, you say you had the larger weight, so you are more to blame for this causing this error. So your weight will be modified more. And this is how weights are modified by propagating the error backwards. And this is how the neural network is trained. As I said, machine learning, this is the usual classification people do. AI is a big overarching set. Machine learning is a subset of this, which includes any machine this can be trained. And then deep learning forms a subset of it. But nowadays, when we call machine learning, we usually do not do this kind of classification. We call traditional machine learning, and by that we mean all those algorithms. There are hundreds of them. If you use Python language, you can go to scikit-learn website and find all of them for regression, for clustering, for classification, or for many other tasks, which use predefined features for doing their work. So we say traditional machine learning is based on those mathematical algorithms. And this deep learning is a newer thing which has happened in the last couple of decades, which has led to actual great successes of AI. Again, I said machine learning, human has to define the features. In deep learning, the network itself learns the features, and it can do the classification based on those features. This year's Nobel Prize in physics went to Hopfield and Hinton. Hinton's group was the one which actually did this first. They came up with this so-called convolutional neural networks, which extract features from images. And based on those features, then, the rest of the neural network, which is densely, fully connected, can do the classification or regression task. So the deep learning is actually the modern big flavor of AI. Then this deep learning was applied to many other, again, biologically inspired things keep on coming up. We have neural networks, then we have addition of memory or recursive neural networks, then long, short-term memory networks. Then Google published an article in Archive called All You Need is an Attention. So mechanism of attention, and which led to neural networks called transformers, actually caused a revolution in NLP, natural language processing. All these large language models that we see nowadays, ChatGPT and all that, they're based on that architecture. So you can see this human-inspired things are actually always leading to big growth. There are many things remaining. We still don't know what it means to be conscious. We have tried to define intelligence, attention, memory, network connections artificially, learning, but we don't know whether neural networks can be self-aware, whether they can dream, whether whether they're conscious. These kinds of things are still there. If we can instill that in a machine, we'll develop something called artificial general intelligence, or even going beyond that, which will be much more intelligent than us, then we'll call it artificial superintelligence. Performance versus data size, deep learning performs much better on larger data, but not so good on a small amount of data. If you have a small amount of data, you might be better off by using traditional machine learning. Now, resurgence of neural networks is because of now we have large amounts of data. As I said, everything is generating a lot of data nowadays. Data availability has become huge, especially for large language models. Internet, all the data available on the internet, in the books and web, has been very, very helpful. So large amount of data is available. Hardware has improved a lot. CPU-based calculations have a limit. Even though we can do threading, there are limitations. Parallelized computations started early to improve the performance of graphics or for gaming. When you have to move large amounts of graphic very quickly on your screen, then another kind of processing was required, and the processor, NVIDIA, we know its name is very famous nowadays. They developed these graphical processing units. Nowadays they call them general processing units because they are now used a lot for AI also, not just for graphics. But the way they speed up graphics calculations is by parallelizing. So instead of like one CPU, you have many parallel tasks going on. So massively parallel computing based GPU hardware, that has driven this growth of deep learning. And nowadays, NVIDIA is swamped with orders. Sharda University recently also acquired a very powerful NVIDIA DGX H100 system. And the waiting time for these is also very long nowadays. I think just a month ago in Mumbai, Jensen Huang, which is a CEO of NVIDIA, and Mukesh Ambani, premier industrialist of India, they both were present. Mukesh Ambani announced that in India they are going to provide a very cheap AI cloud-based access, just like they did with, we used to pay so much for our phone calls earlier. And when Jio came, and suddenly prices went down a lot, now they are going up again. But Mukesh Ambani has said that he plans to do the same for AI, cloud-based AI. So maybe deploying our AI-based models on clouds will become much more cheaper, and that should drive growth a lot in India, at least for AI in near future, if that comes through. And NVIDIA has partnered with Mukesh Ambani, so I think this will happen. And this will be a very good news for India, especially in deploying AI-based solutions. Software developments have also happened. Python programming language nowadays used mostly for AI, and we have many frameworks like TensorFlow, Keras, and PyTorch for AI-based computations. Moore's law is a law which says that computing power grows exponentially by a factor of 2 every couple of years. And you're done, okay. People are saying that Moore's law is actually slowing down because we are reaching the physical limits of how many transistors we can actually pack in a certain amount of space. But Moore's law is being held, that means it still seems to be satisfied because of growth in GPUs. Because GPU-based calculations can still give us this power, so that we can say that Moore's law is still holding. That computer power is doubling every 2 years, is growing exponentially. And this exponential growth of computing power actually has driven AI's growth in near past, and it will continue to make AI grow, as I said, exponentially in near future also. So a lot of big things should be happening not too far in time. Stages of AI, we are at the stage of narrow intelligence. Our AI systems are good at one thing, or a very limited amount of things. AI diagnostics system can identify tumors on MR images very reliably maybe, or ChatGPT can respond for certain things, but it cannot do certain other things. So these are examples of narrow intelligence. So we are at the current stage where our AI is artificial narrow intelligence. Next stage, which Professor Kremchitsky was saying, that artificial general intelligence is coming very soon. So AI will be like us, where it's not just intelligent in doing one task, but like us, it can do many things. It will be like artificial humans kind of capability. Many people think it's not coming very soon or ever, but many people are very, very worried also or enthusiastic also, depending upon the viewpoint, that AGI is coming soon. Next can be AI super intelligent, where the machines become so intelligent that we can't even comprehend what they're doing. Like I give examples of, we can't comprehend what our dogs cannot comprehend what we are doing when we read Kalidasa's poetry or something like that, or some intellectual activity which is completely beyond its capacity to comprehend. So artificial superintelligence can be something like that, and if we make that, then our future will be very strange, to say the least. I'll stop here because in medical technology, as I said, AI is widely used for many kinds of tasks, and in this artificial narrow intelligence has been very successful in medical imaging-based applications for assigning scores and grades of medical abnormalities and all that. Thank you very much.
Any questions? Anyone?
Not agree in the 100% about superintelligence. Humanity will be in risk, because some people this is very pessimistic. Some people very optimistic. I have written a monography in very optimistic style, and what my question is, because you have a very big experience in medicine, why with super intelligence humanity brains like the ant hill cannot be?
Yes, sir. Actually, as I said, some people are very pessimistic, some are very optimistic. And Professor Kemchinski have a very good point here. Why should we, when we see science fiction movies, we think of these alien civilizations which are very advanced than us, and they are very, very violent. They always wish ill to us. They want to destroy us or consume us. But does it have to be so? Would a higher intelligence not be even more benevolent? Or I don't know what to say. So this is in the future. This is beyond our, I mean, we can only guess here. But I agree with you that we cannot just be pessimistic. But I would say that most people are pessimistic about it.
Any other question?
Good evening, sir.
Good evening.
Actually, sir, as you said that just one before slide, as you shown that AGI and ASI is there. So, sir, what do you think about that 2050, that humanity is risk? As you said, that what is your opinion about that? Only that those are having the technical skill, they only will survive. Today also the same scenario. But where you see the world around 2050? Thank you.
Problem is, we are actually, Sri Aurobindo, great philosopher and mystic of India, he used to say that humanity is a work in progress. This is the first time in the history of humanity that mind element has been inserted into evolutionary life at such a level. Before that, mind was only for survival, and now too much brain has been given to us, and we are doing all sorts of things with it, apart from just being using it for surviving. But we are a work in progress. We are just the first experiment in this. And there are lots of conflicts within us as humans, we know. We can have best in us, we can have worst in us. We can be divine, we can be completely evil. Unfortunately for AI, a lot of growth in AI is being driven by armed forces because they get lots of money. They have justification that money spent in defense will save a life of a soldier. But then you can imagine if armies are made of artificial soldiers and a general gets very ambitious, and all kinds of things are plausible. Again, human greed. There's no limit to greed. Greed by definition is, if I have n, I want n plus 1, right? It does not matter whether n is 1 rupee or 1 billion rupees. I just want more. corporate greed, where big corporates can try to use these advanced AI systems to substitute workforce by AI machines, can lead to social upheavals. In the past, all these bad things have not come true, because when computers were introduced in India, a lot of people were very pessimistic, but new kinds of jobs opened up. People think that this will happen here also, but of course, many people are worried. So I come to this point. If humanity has the wisdom to not destroy itself, either through this lust for power or for lust for money or greed, then 2050 will be very good.
Any other question? Can you come here?
First of all, sir, it's a very blissful moment for me to be here and listen to you.
Thank you.
So, myself, Utkarsh Tiwari, and I am from IILM University. And my question to you is, sir, nowadays, machines are learning, but humans are not. Like, previously, when I was in class 6 or 7, I used to have a book which has several letters and essays written on it. And when our teacher used to give us the assignment, we used to read that book, find the format, and then think and write it of our own. But nowadays, if we are missing classes and professors are asking us to write a letter, we are just giving a prompt to ChatGPT or Perplexity, and we are having whole format ready. We are just making the changes and submitting it. Like, we are doing the AI assignment using AI. So, sir, machines are becoming intelligent, and you mentioned those things. So how, as a student, how much AI shall I use, and what should I do to cope up with these things which are upcoming?
Thank you. That's a very good question. The traditional teaching methods will have to give way to something more innovative, because this problem is there everywhere, and not just with students, even people writing any kind of text, including articles. So some people have this mixed view. Why shall not we use help of AI? It's like having a good assistant. Okay, so if I don't want to check my grammar or too much this, I give it to AI, do correct this for me. So using AI as assistant is good. I think it is productive, and it will happen because we cannot wish some things away. Once the genie is out of the bottle, it is out. We cannot put it back again. So this kind of facility is now there with everyone, so people will be using it, right? My only suggestion is that some people have, instead of making ChatGPT as their assistant, they're trying to make it their masters. Okay? They're learning from it. Okay? Don't learn from a LLM. LLM is not wise. LLM is just following some algorithm to generate the next taken and generating all this text from all that information that has been used in its training. You can use it as an assistant, but you must verify and confirm those things yourself. You must not take its output as gospel truth. Don't make it your master, then will be safe. Secondly, our method of exams and education will have to change, I think. We can't work that way. And also, AI gives you now little freedom to work at a higher level. Earlier, we could only walk, or maybe we can ride a horse or some other vehicle of that kind. Now you have cars and autos and aircraft and this and that. So we say we have become lazy because old people were very good, they used to walk, and now we are very bad because we are using cars and this and that. No, what it has done is it has freed us, given us more time to do other things which we could not do then. Earlier, just getting simple things done used to take so much of our time and effort. Now we have a lot of other free time to do many other productive things. Suppose you want to make a little drawing for your paper or a book. You can ask AI to do that. If you do it yourself, you'll be wasting your time. Maybe it won't be so good. Now you can be the director. You don't have to be actor. You can direct AI to bring your vision that you have in your mind to reality. So if you be at that level, higher level, and use AI as your assistant, then that's the most productive way of using this new upsurge of AI tools that we have. Don't make it your master, that whatever it tells you, that's truth. If you want some programs to make AI-generated scientific image, you will know how many mistakes there will be there. Okay.
But it is hampering our thinking level. Like we are not thinking.
No.
Like we need everything. We are getting everything in a structured manner. So as a human, our brain isn't functioning at that level which previously used to.
Actually, I differ with you on that. I know what your concern is, but I do not agree with you on that. I think it's just freeing our mind to do other bigger things. If you're not using that free time, you're wasting your free time in playing games or doing some other, watching TV, then you're wasting that opportunity. But AI is freeing you, giving you more time to do much higher things. Find some new great theorem in mathematics, solve great physics problems or some other things. Use your mind that way. Use AI as assistant. Okay?
Thank you so much.
Okay, welcome.
Any other question?
Yes, sir.
Sir, few studies say that current computational power is not strong enough to support artificial general intelligence. Do you agree with that? If yes, where do we lag and how much time will it take to cope up with that gap?
Actually, it's a very, again, very good question. When we look at science, for example, there is a book by Thomas Kuhn, I think, Kuhn. His book's title is book on scientific philosophy. It's called Structure of Scientific Revolutions. And it says that science does not change slowly. There is a period of growth where stepwise progress is happening. But then big paradigm shifts happen. Things change so suddenly that almost overnight whole view changes. We should be open to such revolutions or paradigm shifts because it has happened in the past, it will definitely happen in the future also. Right now we are limited by, let's say, semiconductor-based devices. Moore's law would have been failing by now, but because the GPU is still holding, right? But new kinds of computing can happen. Quantum computing. Quantum computing can give us a huge advantage, exponential advantage over classical computing in many cases. Molecular computing can happen. All kinds of new computing methods can become available. So we don't know. But we should not preclude that such big shifts cannot happen. 2 years ago, did you think that ChatGPT will happen? Or before that? Didn't you surprise you? So be ready for surprises. And better, don't be on the receiving end. Deliver those surprises by working at a higher level. Right?
Hello, sir. This is MC Khan, and I joined midway. I'm sorry I would have attended the entire speech that you have given. One thing that has struck my mind that God has created angels to serve Him, but angels were not without a free will. Then He created humans with a free will. The angels were capable of doing a lot of work that humans cannot do, but then humans came and they start doing things that the God was not ordering them. So in the field of AI, the ChatGPT is like an angelic phase of that thing. We as a God who created AI, right? So after some time, what happens, first question will AI be having free will in the upcoming years by 2050? And if the AI will be having free will, it will be having some more abilities than humans and human brain. So will it take over humans or will the humanity will be extended? What's your view on that?
It all again comes to what I said, human-like properties, right? Free will is one of those properties. If I look at your free will from outside, I will model it as some statistical, random, stochastic behavior, right? Because I can't predict what you do. Free will means you're not predictable to me, right? So any system which is stochastic appears to sort of have a free will. In classical mechanics, we could say that stochastic systems inherently have well-defined laws, rules to follow. So free will is just apparent, it's not true. Or this randomness is just apparent. It's not that they have some internal free will in them. Chaos theory put a little bit of a dent in that because chaos, even though based on classical mechanics dynamics, introduces unpredictability, even in classical systems, where in theory everything should be predictable. In quantum systems, on the other hand, unpredictability is built in. There, the stochastic nature or random nature of quantum mechanics is not because we don't know something about it. If we know more, we'll figure it out. No, it is inherent. So would you say that electron has free will because it follows quantum mechanics? Right? When we measure it, we can't find out its exactly its position, momentum. So this idea of free will, we have to, like consciousness, free will, idea of self, all those things we have to be clear about when this further growth of AI comes through. But I wouldn't say that machines, even ChatGPT, when it generates its responses, has some stochasticity. You give the same prompt twice, you will not get the same response. There is a parameter in LLMs called temperature parameter, which determines how much randomness will be there in the responses. So again, unless we can define scientifically what is consciousness, what is self, what is free will, it's out there. No? From a behaviorist or from a scientific point of view, free will is shown up as some random behavior, inherent random behavior to outside person.
So one last question from my side, sir.
Yes, sir.
So since I personally know that it's not restricted to AI, but your knowledge goes well into the field of quantum also, and I think at least better than most of us. So I just want to understand what do we see in the future? This AI and quantum, are they going to supplement each other? Will AI need, the way it is increasing, the way we are exploring the features of AI, so will there be a time when we will be completely dependent on quantum computing systems to implement such complex AI algos, or how they are going to do hand in hand, or one thing is going to replace other thing?
Yes, sir. All these things are actually, if you watch science fiction, you see all those things are there in some people's ideas. Quantum mechanics has this weirdness, right? This randomness inherent in it, and superposition, entanglement, all kinds of things are there. Roger Penrose, very famous physicist, he actually proposed with a biologist that consciousness in human brain is quantum. He actually gave some theory, wrote a book also. So people think that consciousness has a quantum angle to it. Right now, science does not define consciousness. Neurobiology books do not define consciousness, right? So whether quantum computing will do something new or whether it will do what actually exists in us, we don't know that right now. But in future, definitely, sir, quantum technologies, when they reach maturity, they will play a big role. And we don't have to depend upon them. Many people are talking about neuromorphic or enhanced. We can have humans enhanced with these kinds of technologies. Elon Musk is already trying that. We'll have a chip or something. So we don't know, sir. I think future is there. We'll see when we see it. Thank you.
Thank you very much, sir. I think of course, we should do it. So we all know, and it's a very common saying that AI is a double-edged sword, and it's all up to us that how do we use it, whether for our benefit or there is good and bad thing of. It's not only about technology. Whatever we do, whatever we see, whatever we have in our life, everything has a good thing and a bad thing. It's all up to us that how do we adopt it, how do we use it, do we become a part of it, or do we keep it aside? So what AI is going to do with us, are we going to make the machines more intelligent, or we are going to be dependent on the machines to become intelligent ourselves? So only the future will come to know only in the future, because the way technology is changing, it's so fast, it's so rapid, it's so random that whatever is going to happen, maybe in a year. 20 years is a long time now. Saying something that, okay, it's going to happen after 20 years, I think it's a very, very long time the way things are changing. 5 years down the line, what is going to happen, nobody knows. So let us hope that this technology is going to make our life better. And that is one of the key themes of this conference, technology and humanity. So the technology is supposed to make our life better, is supposed to help us keeping the humanity alive. And we hope that we will be able to do it because ultimately we are building the technology, we are creating the technology, and we are using it. So it's on both the sides, those who are creating the technology and those who are using the technology. It's a responsibility of both the ends that are we making our life better or not using the technology. Thank you very much for this talk, sir. May I request Dr. Madhukar Deshmukh, the man, one of the key people behind this entire conference who has conceptualized this entire conference, to felicitate the guest speaker. We can have a question now also. Thank you very much. So that's the end for the day for all the 3 tutorials. Thank you very much for being here. As the chair for the pre-conference tutorial and on behalf of the entire WPMC team, I'm heartily thankful to all of you for giving your valuable time for keeping the sessions interactive. Thanks again, and we'll meet again tomorrow with the remaining sessions.